Black holes don't destroy reality, they just swallow it. Clean, final, predictable. Matter crosses the event horizon, information vanishes into the singularity, and the universe moves on. We've made our peace with that particular horror. We've built entire fields of physics around it. But what if we've been staring at the wrong monster this entire time? There is something else out there. Something theorists have been quietly, nervously discussing in the back corners of cosmology conferences for over 2 decades. They call it a Gravastar. And if the math is right, if the physics holds, then scattered throughout the observable universe, there may be objects that make black holes look merciful by comparison. A Gravastar doesn't have a singularity, it doesn't need one. Instead, it traps 1 million solar masses inside a shell of matter that should not exist. Exotic matter. The kind with negative pressure, the kind that bends space-time backward, the kind that creates regions where time itself runs in reverse. No event horizon, no point of no return. Just a surface made of physics so extreme that it tears at the fabric of reality every moment it continues to exist. And here's the truly unsettling part. We can't tell them apart. From the outside, a Gravastar and a black hole look identical. Same gravity, same lensing, same shadow against the stars. Which means every supermassive object we've ever catalogued, every dark giant we've assumed was a black hole, could be something else entirely, something we've been calling by the wrong name for 60 years. The equations that describe Gravastars keep theoretical physicists awake at night. Not because they don't work, because they do. And what they describe is a cosmic predator wearing the mask of something we thought we understood. This is what happens when the universe hides its worst secrets in plain sight. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Black holes terrify us for a very simple reason. They are the place where the rules stop working. Not bend, not stretch, stop. You fall past the event horizon, and every law of physics that kept you tethered to the universe you came from simply gives up. Time ceases to flow forward in any way you would recognize. Space collapses inward toward a singularity where density becomes infinite and volume becomes zero. And once you cross that line, once you drift past that invisible shell of no return, nothing you do, no thrust of a rocket, no burst of energy, no clever trick of navigation will ever get you back out. Light itself cannot escape. And if light cannot escape, then neither can information about what happened to you. You just vanish into the dark, and the universe moves on as if you were never there. That is the familiar terror. We have known about it for more than a century. Carl Schwarzschild calculated the first exact solution to Einstein's field equations in 1916, while serving in the German army during World War I. He was sitting in a trench on the Russian front, dying of an autoimmune disease, and he used what little time he had left to figure out what happens when you compress a star's worth of mass into a small enough volume. The answer he found was so strange that even Einstein did not believe it at first. Schwarzschild's solution predicted a region of space-time so warped that it formed a one-way membrane. Cross it inbound, and you could never leave. For decades, physicists treated the Schwarzschild solution as a mathematical curiosity, a pathological edge case that nature would never actually build. Surely, they thought, something would intervene. Surely the collapse would halt, or the star would explode, or quantum effects would kick in and prevent the formation of this absurd object. They were wrong. By the middle of the 20th century, observational astronomy had gathered enough data to make the picture unavoidable. Stars do collapse. Massive ones, the kind that burn through their nuclear fuel in just a few million years, exhaust every fusion reaction available to them, and then have nothing left to hold themselves up. Hydrogen fuses into helium. Helium fuses into carbon and oxygen. Carbon fuses into neon, sodium, magnesium. The core keeps burning heavier and heavier elements, each stage producing less energy than the one before, until finally the star builds an iron core at its center. Iron is the end of the line. Fusing iron does not release energy, it consumes energy. And once the core is made of iron, the star has run out of fuel. What happens next takes less than a second. The core, no longer supported by the outward pressure of fusion, collapses under its own gravity. Electrons get crushed into protons, forming neutrons and releasing a flood of neutrinos. If the core is light enough, neutron degeneracy pressure, the quantum mechanical resistance that comes from packing neutrons together, can halt the collapse. You end up with a neutron star, a ball of neutrons about 20 kilometers across, weighing more than the Sun. If the core is heavier, even that pressure is not enough. The neutrons themselves cannot hold the weight. The core keeps collapsing. And once it crosses a certain threshold, once the mass concentrated in that shrinking volume exceeds roughly 3 times the mass of the Sun, nothing in the known laws of physics can stop it. The collapse continues all the way down to a singularity, a point of infinite density where space-time itself breaks. Around that singularity, an event horizon forms, the boundary that marks the point of no return. You have made a black hole. The event horizon is not a physical surface. It is not a wall you can touch or a membrane you can see. It is a geometric property of space-time, a place where the curvature becomes so extreme that all future directed paths point inward. Think of it this way. Imagine you are standing on a hill and every direction you can walk leads downhill. No matter which way you turn, no matter how hard you try to climb back up, the slope pulls you down. That is what space-time looks like inside the event horizon. Every direction you can move, including what you think of as forward in time, leads toward the singularity. There is no path out. Not because you are not strong enough or fast enough, because the path does not exist. The size of the event horizon depends on the mass of the black hole. For a black hole with the mass of our Sun, the horizon would sit at a radius of about 3 kilometers. Pack the entire Sun into a sphere 6 kilometers across, and you get a black hole. For a black hole with 10 times the Sun's mass, the radius scales up to 30 kilometers. 1,000 solar masses gives you a horizon 3,000 kilometers across. 1,000,000 solar masses, the kind you find lurking at the centers of galaxies, gives you a horizon roughly 3 million kilometers in radius. That is about 4 times the distance from the Earth to the Moon. A sphere of space-time, 4 lunar distances wide, and if you cross it, you are never coming back. Tidal forces near a black hole are where the horror gets visceral. Gravity does not pull uniformly. It pulls harder on things that are closer. Stand near a black hole and your feet, assuming they are pointing toward the singularity, experience stronger gravity than your head. The difference stretches you. For a stellar mass black hole, the kind formed from a collapsing star, that stretching becomes extreme very quickly. Long before you reach the event horizon, the difference in gravitational pull between your head and your feet would be enough to tear you apart. Physicists call this spaghettification, which is a terrible name for a process that turns your body into a thin stream of atoms. You do not fall into a black hole as a coherent object. You fall in as a thread of disassembled matter, stretched thinner and thinner, until individual atoms are ripped away from each other. For supermassive black holes, the ones weighing millions or billions of solar masses, the tidal forces at the event horizon are surprisingly gentle. The horizon is so far from the singularity that the curvature of spacetime is almost flat at that distance. You could cross the event horizon of a billion solar mass black hole and feel nothing. No stretching, no tearing, no sudden violence. You would drift across in perfect comfort, entirely unaware that you had just passed the point of no return. Only later, as you fell deeper and the tidal forces grew stronger, would your body begin to stretch. By then, it would be far too late. The singularity would be waiting, and nothing you could do would change your trajectory toward it. We have never seen a black hole directly. We cannot. Black holes do not emit light. They do not reflect light. They are, by definition, invisible. What we see instead is everything around them. Gas falling toward a black hole heats up through friction and compression, glowing brightly in X-rays before crossing the horizon. Stars orbiting close to a black hole move faster than they should, their velocities betraying the presence of an enormous unseen mass. Light passing near a black hole bends, following the curved spacetime around it. This is gravitational lensing, and it is one of the most direct pieces of evidence we have that black holes exist. Gravitational lensing happens because mass warps spacetime, and light follows that warped geometry. Picture spacetime as a rubber sheet stretched flat. Drop a heavy ball onto the sheet, and it sags, creating a dip. Roll a marble past the dip, and its path curves, bending around the heavy ball, even though the two never touch. Light does the same thing around a massive object. A black hole, being the most compact massive object you can have, creates the deepest possible dip. Light passing close to it bends sharply, sometimes looping entirely around the black hole before escaping. If you position yourself just right, you can see multiple images of the same background star, each image following a different light path that curved around the black hole. Some images appear brighter, some appear stretched into arcs or rings. Some disappear entirely, hidden behind the black hole's shadow. The shadow is real. It is the dark region at the center of the lensed light, where photons either fell into the event horizon or looped so many times around the black hole that they never made it out. The shadow is slightly larger than the event horizon itself because light orbiting just outside the horizon gets trapped in unstable circular paths. From a distance, that trapped light creates a dark circle roughly 2.5 times the size of the event horizon. That shadow is what telescopes can image. And in 2019, a global network of radio dishes called the Event Horizon Telescope produced the first direct image of a black hole's shadow, a glowing ring of light surrounding a dark center, sitting at the heart of the galaxy Messier 87. The image confirmed decades of predictions. The math was right, the models were right. Black holes exist, and they look exactly the way general relativity said they should. That should be the end of the story. Black holes are real. We understand how they form. We understand how they behave. We have imaged them. Problem solved. Except there is a crack running through the foundation of that understanding, and the crack has been widening for more than 50 years. Physicists call it the black hole information paradox, and it is one of the deepest unresolved problems in all of physics. The paradox is simple to state and impossible to resolve. Quantum mechanics says that information cannot be destroyed. If you know the exact quantum state of a system at one moment, the laws of physics allow you to calculate its state at any future or past moment. Information is conserved, always. That principle, called unitarity, is the bedrock of quantum theory. Break it and the entire framework collapses. Black holes appear to violate unitarity. When matter falls past the event horizon, all the information encoded in that matter, every quantum detail about the particles that made it up, seems to vanish. The black hole does not care what fell in: a star, a planet, a book, a hard drive full of data. It makes no difference. Once the matter crosses the horizon, the only things the black hole remembers are its total mass, its electric charge, and its angular momentum. Everything else is gone. Physicists summarize this with a phrase that sounds almost flippant: black holes have no hair, meaning they have no distinguishing features beyond those three numbers. All the complexity, all the information that made the infalling matter unique erases itself behind the event horizon. That would be strange but acceptable if black holes lasted forever. Information could be hidden but not destroyed. The paradox comes from Stephen Hawking's discovery in 1974 that black holes are not eternal, they radiate. Quantum effects near the event horizon allow particle-antiparticle pairs to form from the vacuum. Normally, these pairs annihilate each other almost immediately, but near a black hole, one particle can fall in while the other escapes. To an outside observer, it looks like the black hole is emitting radiation, Hawking radiation. The radiation carries energy away from the black hole, which means the black hole loses mass. Over an unimaginably long timescale, trillions upon trillions of years for a stellar mass black hole, the radiation evaporates the entire black hole. When the black hole is gone, all that remains is the thermal radiation it emitted. And thermal radiation carries no information. It is random, structureless, determined only by temperature. The information that fell into the black hole has been destroyed. That is the paradox. Quantum mechanics forbids the destruction of information. Black hole evaporation appears to destroy it anyway. One of the two frameworks, quantum mechanics or general relativity, must be wrong, or incomplete, or hiding something we have not figured out yet. Claudia D. Rahm and Chris Engelhardt, writing for MIT Physics, describe it as a conflict between two apparently incontrovertible facts. The Stanford Encyclopedia of Philosophy calls it one of the most fundamental challenges linking general relativity, quantum mechanics, and thermodynamics. Decades of work by some of the smartest physicists alive have not resolved it. Proposals range from information somehow encoding itself on the event horizon to quantum entanglement between the interior and exterior of the black hole, preserving information in ways we do not yet understand. Every solution requires either modifying quantum mechanics, modifying general relativity, or accepting that something deeply strange happens at the horizon that current physics cannot describe. The existence of the paradox tells us something uncomfortable. Black holes, for all their terrifying certainty, sit at the edge of what we actually understand. The singularity at the center is a place where our equations break down, where density becomes infinite and the laws of physics stop making predictions. The event horizon, that clean geometric boundary, may be hiding processes that violate principles we thought were inviolable. And if black holes, the most studied and well-understood extreme objects in the universe, still contain mysteries that break our theories, then the door is open. Open to what? To the possibility that black holes are not the only kind of collapsed object nature can build. To the possibility that there are other things out there, other configurations of mass and spacetime that are even stranger, even more extreme. To the possibility that the universe has not finished showing us what happens when you push matter and energy to their absolute limits. Some researchers argue that the paradox depends on idealized models of collapse, that observer-dependent descriptions or extensions of spacetime beyond the singularity could resolve the tension. Others suggest that singularities themselves may not be real, that they are artifacts of classical general relativity that quantum gravity will smooth out once we figure out what quantum gravity actually is. But we do not have a theory of quantum gravity. We have candidates: string theory, loop quantum gravity, causal set theory. None of them are complete. None of them make testable predictions we can check. And in the absence of a working theory, the singularity remains a wall, a boundary where known physics ends and speculation begins. Black holes are not the ultimate limit. They are the limit of what we have confirmed. The difference matters, because if the information paradox is telling us that something is missing from our understanding of collapsed objects, then maybe, just maybe, there is another kind of object waiting in the dark. One that does not have an event horizon, one that does not have a singularity, one that obeys different rules, stranger rules, rules we have only begun to sketch out in the mathematics. An object that looks like a black hole from the outside, but is built from something else entirely on the inside. A cosmic predator that wears a black hole's face, but hides a deeper, more unsettling reality beneath. That object has a name, and the formation process that might create it begins where black holes begin. In the violent death of a massive star, at the moment when the core collapses and reality itself starts to buckle under the weight. The death of a massive star is not a slow fade. It is not a gentle dimming, not a gradual winding down into darkness. It is a catastrophe that takes less time than it takes you to blink, and the catastrophe is not random. It is written into the physics of how stars work, locked into the structure of matter itself, waiting patiently inside every star massive enough to trigger it. The star spends millions of years building toward this moment, and when the moment arrives, the star has about 1 second to decide what it becomes next. Start with a star, not a small one, not something modest like our sun, a massive star, 10 times the sun's mass at minimum, 20, 30, 50 times if you want the full spectacle. Stars like this are rare. They make up less than 1% of all stars in the galaxy, but they are the ones that matter for this story, because they are the only ones that die hard enough to create the kinds of objects we are about to discuss. A massive star burns hydrogen into helium in its core, the same fusion reaction that powers our sun. But where the sun will spend 10 billion years doing this, a star 50 times more massive burns through its hydrogen in just a few million years. The reason is pressure. The core of a massive star is unimaginably hot and dense. Temperatures reach tens of millions of degrees. The pressure is so intense that hydrogen nuclei, which normally repel each other because they are both positively charged, get forced close enough together that the strong nuclear force takes over and fuses them into helium. Every fusion reaction releases energy. That energy pushes outward, holding the star up against the inward crush of its own gravity. As long as the core keeps fusing hydrogen, the star remains stable, a balance between the pull of gravity and the push of fusion pressure. Hydrostatic equilibrium. The star can sit in that balance for millions of years, shining steadily, doing nothing remarkable except existing. Then the hydrogen runs out. Not everywhere. The outer layers of the star still have plenty of hydrogen, but the core, the central furnace where fusion happens, exhausts its supply. Fusion stops, the outward pressure drops, gravity wins, the core contracts. And here is where things get interesting. When you compress a gas, it heats up. The core of the star, now collapsing under its own weight, heats up enough to ignite the next reaction, helium fusion. 3 helium nuclei fuse into carbon, releasing energy and re-establishing the pressure that holds the core up. the star stabilizes again, but not for long. Helium fusion is less efficient than hydrogen fusion. It does not release as much energy per reaction. The star burns through its helium much faster than it burned through its hydrogen. A star that spent 3 million years fusing hydrogen might spend only a few 100,000 years fusing helium. Then the helium runs out, the core contracts again, the temperature climbs, carbon fusion ignites, carbon fuses into neon, sodium, magnesium. The star burns through that in a few thousand years. Neon fuses into oxygen, that lasts a few years. Oxygen fuses into silicon, that lasts a few months. Silicon fuses into iron, that lasts about 1 day. Iron is the end. Fusing elements lighter than iron releases energy because the resulting nucleus is more tightly bound than the original pieces. The mass difference, that tiny lost fraction of mass, converts into energy according to Einstein's equation. Energy equals mass times the speed of light squared. A little bit of mass becomes a lot of energy. That energy supports the star, but iron is at the peak of the binding energy curve. Fusing iron into anything heavier does not release energy, it costs energy. You have to put energy in to make the reaction happen. The core of the star, now made almost entirely of iron, has no more fuel. There is no next reaction to ignite. Fusion stops, the pressure vanishes, and gravity, which has been waiting patiently for millions of years, takes over. What happens next is so fast that calling it an explosion almost misses the point. The core collapses, not slowly, not gradually. The iron core, no longer supported by fusion pressure, falls inward on itself at roughly 1/4 the speed of light, 25% of light speed. In less than 1 second, a core the size of Earth compresses down to the size of a city. The density climbs from a few 100 grams per cubic centimeter to 1 trillion grams per cubic centimeter. The temperature spikes to hundreds of billions of degrees. The pressure becomes so extreme that atomic nuclei cannot hold themselves together anymore. Electrons, which normally orbit the nucleus in neat quantum shells, get crushed into the protons. Electron plus proton equals neutron plus neutrino. The core floods with neutrinos, ghostly particles that barely interact with anything. Under normal circumstances, neutrinos pass through matter like it is not even there. A neutrino can fly through a light year of solid lead without hitting anything. But the collapsing core is so dense that even neutrinos get trapped for a moment. Then they burst out, carrying away most of the energy of the collapse in a flood so intense that it blows the outer layers of the star into space. That is the supernova, the visible explosion, the blast wave that lights up the sky. But the supernova is a side effect. The real story is happening in the core. The core is now made of neutrons. Neutrons packed so tightly together that they are touching. Neutron degeneracy pressure, the quantum mechanical resistance that comes from the Pauli exclusion principle, says that you cannot put two identical fermions in the same quantum state. Neutrons are fermions. When you try to compress them past a certain point, they push back, not because of any force in the traditional sense, because the mathematics of quantum mechanics forbids you from packing them any tighter without promoting them to higher energy states. That promotion costs energy, and the requirement to pay that energy cost translates into pressure, degeneracy pressure. For a core that is not too heavy, degeneracy pressure is enough. The collapse halts. You end up with a neutron star, a ball of neutrons about 20 kilometers across, weighing between 1 and 2 times the mass of the Sun. Neutron stars are the densest objects in the universe that are not black holes. A sugar cube of neutron star material would weigh about 1 billion tons. The entire mass of humanity, all 8 billion people, would fit into a sphere the size of a grain of sand if compressed to neutron star density. But there is a limit. Subramanian Chandrasekhar calculated the first version of this limit in the early 1930s, working on the problem of white dwarf stars. White dwarfs are supported by electron degeneracy pressure, not neutron degeneracy pressure, but the physics is similar. Chandrasekhar showed that there is a maximum mass a white dwarf can have before electron degeneracy pressure fails. The limit sits at about 1.4 solar masses. Pack more mass than that into a white dwarf, and the electrons cannot hold it up. The object collapses further. For neutron stars, the limit is higher, but not by much. J. Robert Oppenheimer and George Volkoff calculated it in 1939. The Tolman-Oppenheimer-Volkoff limit, the TOV limit. Oppenheimer is better known for leading the Manhattan Project, but before the war, he was a theoretical physicist working on the problem of what happens to the cores of collapsing stars. He and Volkoff used the equations of general relativity to ask a simple question: how much mass can you pack into a neutron star before neutron degeneracy pressure fails? The answer they got was roughly 0.7 solar masses. That number turned out to be too low. Later calculations using better equations of state for neutron matter pushed the limit higher. Modern estimates place the TOV limit somewhere between 1.5 and 3 solar masses, depending on the exact properties of matter at nuclear densities. Nobody knows the precise value because nobody has ever been able to recreate those densities in a lab. The conditions inside a neutron star are more extreme than anything we can test on Earth. The best we can do is build models, run simulations, and compare the predictions to observations of real neutron stars. The observations suggest the limit is probably somewhere around 2 solar masses, maybe a bit higher, but the uncertainty is real. We are extrapolating from physics we understand into a regime where we are not entirely sure the physics behaves the way we think it does. What happens if the core exceeds the TOV limit? The standard answer is simple. The core keeps collapsing. Neutron degeneracy pressure fails. There is no other known force or pressure strong enough to stop the collapse. The core shrinks past the point where it could be a neutron star. It keeps shrinking. General relativity says that if you compress enough mass into a small enough volume, space-time warps so severely that you form an event horizon. Once the event horizon forms, the collapse cannot stop. The core continues shrinking inside the horizon until it reaches zero volume, infinite density, a singularity. You have made a black hole. That is the story every textbook tells. And it is probably right, probably. But the word probably is doing a lot of work, because the singularity is a problem, not a small problem, a foundational problem. When density becomes infinite, the equations of general relativity break down. They stop giving finite answers. The curvature of spacetime at the singularity is infinite. The tidal forces are infinite. Infinities in physics are usually a sign that something has gone wrong. Not that the universe has broken, that your theory has reached its limit. General relativity is a classical theory. It does not include quantum mechanics. And at the scales where singularities form, quantum mechanics absolutely matters. The singularity is telling us that we are trying to use a tool outside its range of validity. We are extrapolating general relativity into a regime where it cannot be trusted. Physicists have known this for decades. The singularity theorems, proven by Roger Penrose and Stephen Hawking in the 1960s, show that singularities are a generic feature of gravitational collapse in general relativity. They are not special cases or rare outcomes. They are what the math predicts will happen whenever you compress enough matter into a small enough space. But the singularity theorems also assume that general relativity is the correct description of spacetime, all the way down to arbitrarily small scales, and there is no good reason to believe that assumption. Quantum mechanics becomes important at very small scales. The Planck length, about 10 to the power of -35 meters, is the scale where quantum gravitational effects should dominate. The singularity, if it exists, sits at a scale far smaller than that. Asking what happens at the singularity is like asking what the temperature was at the exact instant of the Big Bang. The question assumes a level of precision that our theories do not support. So maybe the singularity is not real. Maybe something else happens. Maybe the collapse halts just before the singularity forms, stabilized by some exotic quantum effect we do not yet understand. Maybe spacetime itself has a minimum size, a granular structure that prevents density from becoming truly infinite. Maybe the equations of state for matter at these densities allow for pressures and stresses we have not accounted for. These are not wild guesses. They are serious proposals being studied by serious physicists, but they are speculative. There is no experimental evidence for any of them. We have never observed matter at densities anywhere close to what you would find inside a collapsing core. We have never measured the equation of state for neutron matter beyond a certain threshold. We are flying blind. One possibility is exotic matter, not exotic in the sense of unusual, exotic in the technical sense that it violates assumptions we normally make about how matter behaves. Normal matter has positive energy density. The more of it you have, the stronger its gravitational pull. Exotic matter, depending on how you define it, could have negative energy density or negative pressure or some combination of properties that allows it to push outward instead of pulling inward. If exotic matter exists, and if it can form under the extreme conditions inside a collapsing stellar core, it might be able to halt the collapse before a singularity forms. You would end up with an object held up not by degeneracy pressure, but by something else, something stranger. An object that looks like a black hole from the outside, but has a completely different internal structure. No singularity, no event horizon. Just a shell of exotic matter balanced against the inward pull of gravity. There is no experimental evidence for exotic matter. Let me repeat that because it matters. There is no experimental evidence for exotic matter. We have never detected it in a lab. We have never observed it in space. Every particle we have ever measured has positive energy density. Exotic matter is allowed by the equations of general relativity in the same way that warp drives and wormholes are allowed. The math does not forbid it. But the math not forbidding something is very different from nature actually building it. General relativity is full of solutions that are mathematically valid but physically unrealizable. The question is not whether exotic matter is consistent with general relativity. The question is whether it exists, and we do not know. Quark stars are another possibility. Under normal conditions, quarks are confined inside protons and neutrons. You cannot pull a single quark out of a proton and hold it in your hand. The strong force, the interaction that binds quarks together, gets stronger the farther apart you try to pull them. Try to separate two quarks, and the energy you put in eventually becomes large enough to create a new quark-antiquark pair. You end up with two bound particles instead of two free quarks. But at extremely high densities, the kind you find in the core of a collapsing neutron star, quarks might deconfine. The protons and neutrons dissolve. The quarks mix together into a soup, a quark-gluon plasma. Some theoretical models suggest that this deconfined quark matter could be more stable than neutron matter under certain conditions. If that is true, the core of a collapsing star above the TOV limit might not collapse all the way to a black hole. It might stop at a quark star, a ball of quark matter held up by quark degeneracy pressure. Quark stars would be slightly smaller and slightly denser than neutron stars, but still finite in size. No singularity, no event horizon. Again, there is no experimental evidence. We have created quark-gluon plasmas in particle accelerators, but only for tiny fractions of a second, and only at much lower densities than what you would find inside a collapsing core. We have no idea whether stable quark matter can exist at the densities required to support a stellar remnant. The equations of state for quark matter are uncertain. The phase transition from neutron matter to quark matter is not well understood. Some models predict that the transition would release so much energy that it would trigger a supernova by itself. Other models predict that quark stars cannot exist at all because quark matter is less stable than neutron matter at every density. The jury is out. Then there is the possibility of a naked singularity. Most solutions to the equations of general relativity that contain singularities also contain event horizons. The singularity is hidden behind the horizon, invisible to the outside universe. Roger Penrose proposed the cosmic censorship hypothesis in 1969, suggesting that nature does not allow naked singularities to form. Every singularity, Penrose argued, is clothed by an event horizon. But cosmic censorship is a conjecture, not a proven theorem, and there are known solutions to the Einstein equations that violate it. Certain types of rotating collapse, under very specific conditions, can produce singularities without event horizons. A naked singularity would be visible. You could, in principle, watch it form. You could see space-time curvature becoming infinite at a point. And you could, in theory, send signals to and from the singularity without crossing an event horizon. Whether nature actually allows this is an open question. Most physicists suspect that cosmic censorship is correct, that some mechanism we do not understand steps in to prevent naked singularities from forming. But suspecting something and proving it are different things. The final fate of a collapsing stellar core in some theoretical frameworks could be a naked singularity, or it could be a black hole, or it could be something else entirely. The uncertainty is not a bug, it is the point. We do not know what happens when you compress matter past the TOV limit because we have never been there. We cannot recreate those conditions. We cannot run the experiment. We can observe the aftermath, the black holes and neutron stars scattered across the galaxy, but we cannot watch the collapse happen. The event itself is hidden, either behind an event horizon or inside a supernova, or both. The best we can do is build models and check whether the models match the observations. And the observations are frustratingly consistent with multiple possibilities. Some neutron stars are spinning at more than 700 rotations per second, pulsars, lighthouses made of neutrons, beaming radiation into space every time they spin. The fastest ones push right up against the theoretical limits of how fast a neutron star can rotate before it flies apart. Measuring their masses gives us clues about the equation of state for neutron matter. If a neutron star weighing 2 solar masses is stable, the TOV limit must be at least 2 solar masses. If we ever detect a neutron star heavier than 3 solar masses, we would know something strange is happening. Either the equation of state is stiffer than expected, meaning matter at nuclear densities pushes back harder than we thought, or the object is not a normal neutron star. It could be a quark star. It could be something else. The line between what is possible and what is not sits frustratingly close to the edge of what we can measure. Meanwhile, stellar mass black holes are common. We have detected dozens of them through gravitational wave observations. When two black holes merge, they ripple spacetime itself, sending waves outward at the speed of light. The LIGO and Virgo detectors have been catching those waves since 2015. Every detection gives us the masses of the merging black holes. Most of them fall in a narrow range, 5 to 50 solar masses. A few are heavier. The heaviest stellar mass black hole detected so far weighs about 85 solar masses. None of them are lighter than about 5 solar masses. That gap, the desert between the heaviest neutron stars and the lightest black holes, is telling us something. Either stellar collapse does not produce objects in that mass range, or those objects are rare enough that we have not detected them yet, or they exist, but they are not black holes. They are something else, something that does not emit gravitational waves the way black holes do. The core of a massive star, in the final moments before collapse, is a laboratory for physics we cannot replicate anywhere else. Densities higher than atomic nuclei, temperatures higher than the cores of the hottest stars, pressures that dwarf anything we can create in a particle accelerator, and timescales so short that the entire collapse happens faster than a neutrino can travel from the center of the core to the edge. We think we know what happens. The textbooks are confident, the models are detailed, but confidence is not certainty, and the gap between what we can calculate and what we can confirm experimentally is enormous. The gap is where the next object enters the story. Not a black hole, not a neutron star, something else, something that exists only on paper, at least for now, but on paper it exists with enough mathematical rigor to have survived 2 decades of scrutiny without being definitively ruled out. The object has a name that sounds like it was designed to intimidate: Gravastar, short for gravitational vacuum condensate star. And if the theory behind it turns out to be correct, then the universe has been hiding monsters that make black holes look almost benign by comparison. The Gravastar hypothesis was first proposed in 2001 by Paul Mazur and Emil Mottola, 2 physicists working at the intersection of quantum field theory and general relativity. They were not trying to invent a new kind of star. They were trying to solve a problem: the black hole information paradox. The paradox that says information cannot be destroyed, but black holes appear to destroy it anyway. Mazur and Mottola looked at the paradox and asked a simple question: what if black holes do not actually form? What if the collapse stops just before the event horizon appears? What if instead of falling into a singularity, the collapsing matter hits a wall, a barrier made of something so exotic that it can push back against gravity hard enough to halt the collapse entirely? They ran the math. The math said it could work. Under very specific conditions, with very specific assumptions about the behavior of matter at extreme densities, you could build an object that looks like a black hole from the outside but has no event horizon and no singularity. You could avoid the paradox entirely by avoiding the black hole. The name itself is a clue to what is happening inside. Gravitational vacuum condensate star. Break that down. Gravitational. The object is held together by gravity, same as any star or compact object. Vacuum condensate. This is where things get strange. In quantum field theory, the vacuum is not empty. It is a seething foam of virtual particles popping in and out of existence, borrowing energy from the uncertainty principle and paying it back before anyone notices. Under normal conditions, the vacuum has no net effect. The energy density averages to 0, but under extreme gravitational stress, the kind you find in a collapsing stellar core, the vacuum can undergo a phase transition. Think of water freezing into ice, same molecules, different structure, different properties. The vacuum, in this picture, condenses into a new state, a state with negative pressure, a state that pushes outward instead of pulling inward, a state that can hold up the collapsing core without requiring degeneracy pressure or any other conventional source of support. Star. Because it is still a stellar remnant, still the core of a dead massive star, just not the kind of remnant anyone expected. The original Mazur-Mottola model divides a Gravastar into 3 regions. Start from the outside and work your way in. The outermost region is ordinary vacuum, Schwarzschild spacetime, the same curved geometry you find around any spherical mass. From a distance, this region looks exactly like the exterior of a black hole. The curvature matches, the gravitational lensing matches, light bends the same way, stars orbit the same way. If you point a telescope at a Gravastar from a few million kilometers away, you see a dark object surrounded by a ring of lensed light. Exactly what you would see if you looked at a black hole. The Gravastar is wearing a mask, a perfect mask, and the mask is not a disguise. It is what general relativity predicts you should see when you pack that much mass into that small a volume. The Gravastar and the black hole produce identical external spacetimes because they have identical masses and identical sizes. The difference is inside. Move inward and you hit the second region, a shell, thin, unimaginably thin, but not zero thickness. This is the critical layer, the boundary between the outside universe and the interior. In the Mazur-Mottola model, this shell is made of ultra-relativistic matter, matter moving at speeds so close to the speed of light that its pressure equals its energy density. The equation of state for this shell is pressure equals energy density. That is not a normal equation of state. Normal matter has pressure much smaller than its energy density. Even inside a neutron star, the pressure is only a small fraction of the energy density. But in the shell of a Gravastar, the two are equal. The shell is under enormous tension, stretched tight like a drumhead, holding the interior in and keeping the exterior out. This shell is doing the work that the event horizon does in a black hole. It is the boundary, but it is a physical boundary, not a geometric one. You can touch it, in principle. If you could survive the approach, which you could not, because the tidal forces near the shell would rip you apart long before you got close. But the shell is real. It is made of matter. It has a surface. It has tension. The tension is what holds it up. The shell pushes outward with enough force to balance the inward pull of gravity. The balance is exact. If the tension were slightly weaker, the shell would collapse. If it were slightly stronger, the shell would explode. The Gravastar sits at the knife edge between the two, a pressure equilibrium so precise that it makes a neutron star look stable by comparison. Now move inward past the shell, and here is where the model stops making intuitive sense. The interior is not matter. It is not neutrons, not quarks, not any form of particle you would recognize. It is vacuum, but not the vacuum you find in interstellar space. This is a different kind of vacuum, a false vacuum, a state with negative energy density, or more precisely, a state where the pressure is equal to minus the energy density. The equation of state for the interior is pressure equals negative energy density. That is the equation of state for dark energy. The same stuff that is currently accelerating the expansion of the universe. Inside a Gravastar, the core is filled with dark energy, not metaphorically, literally. The vacuum has condensed into a state that behaves exactly like the cosmological constant, the term Einstein added to his equations to allow for a static universe and later called his biggest blunder. Except inside a Gravastar, that term is not a blunder. It is the entire reason the object exists. Dark energy pushes. That is what it does. The expansion of the universe is accelerating because dark energy has negative pressure, and negative pressure in general relativity produces a repulsive gravitational effect. The same thing happens inside a Gravastar. The dark energy core pushes outward, counteracting the inward pull of gravity. The push is strong enough to prevent the core from collapsing into a singularity. The core does not shrink to zero volume. It stops at a finite size, held open by the negative pressure of the vacuum condensate. No singularity, no point of infinite density. Just a region of space-time filled with exotic vacuum energy, sitting quietly inside the shell, keeping the whole structure stable. This is not speculation in the sense of making things up. The Mazur-Mottola model is a solution to the Einstein field equations. It satisfies general relativity. The geometry is consistent. The stress-energy tensor is well defined. The boundary conditions match. If you plug the numbers into the equations, they work. The Gravastar is mathematically allowed. That does not mean it is real. It means it is not forbidden. And in physics, that distinction matters. The key word in all of this is exotic. Exotic matter, exotic vacuum, exotic equation of state. The word exotic is a technical term. It does not mean unusual or interesting. It means the matter violates the energy conditions that normal matter obeys. There are several energy conditions in general relativity, mathematical statements about the relationships between energy density and pressure that ordinary matter satisfies. The weak energy condition says that energy density must be non-negative in every reference frame. The strong energy condition says that energy density plus pressure must be non-negative. The dominant energy condition says that energy density must be at least as large as pressure. Normal matter, everything you have ever touched or seen or measured, obeys all of these. Exotic matter violates at least one of them. The dark energy core of a Gravastar violates the strong energy condition because the pressure is negative. The shell, with its equation of state pressure equals energy density, sits right at the boundary of what the energy conditions allow. The Gravastar as a whole is built from matter that behaves in ways that no known form of matter behaves. Does exotic matter exist? That is the question. And the answer, frustratingly, is maybe. We have never detected exotic matter in a lab. Every particle we have ever measured has positive energy density. Every substance we have ever studied obeys the energy conditions. But there are hints. The expansion of the universe is accelerating, and the only way to explain that acceleration within the framework of general relativity is to invoke something with negative pressure. We call it dark energy, and we have no idea what it actually is. It could be a cosmological constant, a property of space-time itself. It could be a field, something like the Higgs field, but with different properties. It could be something else entirely. Whatever it is, it behaves like exotic matter on cosmological scales. The question is whether it can exist in concentrated form. Whether you can take the same stuff that is accelerating the universe and pack it into a ball 20 kilometers across. The equations allow it. Nature might not. Some theoretical models suggest that the vacuum can undergo phase transitions under extreme conditions. The idea is similar to how water can exist as ice, liquid, or vapor, depending on temperature and pressure. The vacuum in these models has multiple possible states. The state we live in, the one we call empty space, is the lowest energy state. But there could be higher energy states, false vacuums, that are stable under certain conditions. If the collapsing core of a massive star creates the right conditions, temperature, density, curvature, the vacuum could flip from the normal state into a false vacuum state. The phase transition would release energy, but not in the form of heat or radiation. The energy would go into the vacuum itself, giving it the negative pressure needed to halt the collapse. You would end up with a core of false vacuum surrounded by a shell of stressed matter, a gravastar. The process would happen fast. The core collapse takes less than a second. The vacuum phase transition, if it happens, would happen even faster. The collapsing matter hits the transition point. The vacuum flips. The pressure goes negative. The collapse stops. From the outside, you would see a supernova. The outer layers of the star explode. But instead of leaving behind a black hole, the remnant would be a gravastar, a dark, compact object, invisible except for its gravitational effects, identical in appearance to a black hole but fundamentally different in structure. And here is the unsettling part. We would not be able to tell the difference, not easily. The gravitational field outside a gravastar is the same as the gravitational field outside a black hole of the same mass. The lensing is the same. The orbits of nearby stars are the same. The only way to distinguish them would be to look for subtle differences in how they interact with infalling matter or how they respond to tidal forces from nearby objects, and those differences are small. Small enough that with current technology we might not be able to detect them. So it is possible, just barely possible, that some of the black holes we have been observing for decades are not black holes at all. They are gravastars, objects that formed in the final moments of stellar collapse when the vacuum underwent a phase transition and exotic matter flooded the core. Objects that have been sitting quietly in the dark, mimicking black holes so perfectly that we have never noticed the difference. The thought is uncomfortable, not because gravastars are dangerous in any immediate sense, they are not going to reach out and grab us, but because they represent a kind of cosmic deception, an entire class of objects hiding in plain sight, wearing the face of something we thought we understood. The Mazar-Mottola paper landed in 2001. It was not ignored. It was published in the Proceedings of the National Academy of Sciences, a serious journal. Other physicists read it, checked the math, and started exploring the idea. In 2003, another paper appeared, this one by a different team, analyzing the stability of gravastars. The conclusion was cautiously optimistic. Gravastars could be stable under certain conditions. They would not collapse into black holes. They would not explode. They would just sit there, balanced on the edge between collapse and expansion, held together by the tension in the shell and the negative pressure in the core. The paper called the Gravastar hypothesis one of a very small number of serious challenges to our usual conception of a black hole. That phrasing is worth sitting with. A serious challenge, not a curiosity, not a fringe idea, a challenge. The authors were not claiming gravastars exist. They were claiming the possibility could not be ruled out. Over the next 2 decades, more papers followed. Some explored variations on the original model. Some asked whether gravastars could form through mechanisms other than vacuum phase transitions. Some studied what would happen if 2 gravastars collided, or if a gravastar accreted matter from a companion star. The literature grew. The idea did not go away. And the reason it did not go away is that the problem it was designed to solve, the information paradox, also did not go away. Black holes still appear to destroy information. Physicists still do not have a satisfactory resolution. And as long as that paradox sits unresolved, alternatives like gravastars remain on the table. One of the more striking claims in the popular literature is that a gravastar the size of a city, something roughly as wide as London, could weigh about 10 solar masses. That is the same mass packed into the same volume as a stellar mass black hole. The compactness is identical. The only difference is the internal structure. Where a black hole has a singularity, the gravastar has a core of dark energy, Where a black hole has an event horizon, the Gravastar has a shell of ultra-relativistic matter. The numbers work, the geometry fits. The Gravastar can be just as compact, just as dense, just as dark, without being a black hole, and that is the point. Maximum compactness without a singularity. All the gravitational terror of a black hole without the information-destroying event horizon. The Gravastar is described in technical papers as a cold, low-entropy, maximally compact object with a surface boundary layer and physical surface tension. That last phrase is important, surface tension. The shell is holding itself together the way a soap bubble holds itself together. Except the bubble is made of matter under pressures that exceed anything inside a neutron star, and the bubble is wrapped around a core of spacetime that is trying to push outward with the force of dark energy. The tension in the shell is what keeps the whole thing from flying apart or collapsing inward, and the balance is so delicate that even small perturbations could destabilize it. What happens if the balance breaks? The models do not agree. Some suggest the Gravastar would collapse into a black hole after all. The shell fails, the core implodes, and the singularity forms. Others suggest the Gravastar might explode, releasing the vacuum energy in a burst that could rival a supernova. Still others propose that the object might settle into a different configuration, a pulsating state or a rotating state where the shell oscillates or the core shifts. Nobody knows. The predictions depend on details of the equation of state and the stability of the vacuum condensate that we do not have experimental access to. The Gravastar, if it exists, is exploring a regime of physics we cannot test. And here is the thing that makes Gravastars more unsettling than black holes. A black hole is simple, brutally simple. 3 numbers: mass, charge, spin. Everything else erases. A Gravastar is complicated. It has layers, it has structure. It has an interior that depends on the properties of exotic matter and false vacuums and phase transitions we barely understand. A black hole is a geometric object. A Gravastar is a physical object. And physical objects can do things geometry cannot. They can pulse, they can resonate, they can have modes of oscillation. If Gravastars exist, they might ring like bells when disturbed, emitting gravitational waves with frequencies and patterns that do not match black hole ringdowns. That would be the smoking gun, the signal that tells us something is different. But detecting that signal requires gravitational wave detectors more sensitive than anything we have today. The differences are subtle, buried in the fine details of the waveform, and until we can measure those details with enough precision, Gravastars and black holes will continue to look the same. The hypothesis is still theoretical. That needs to be said clearly. Gravastars are hypothetical condensed objects. They have not been observed. They have not been confirmed. Every compact object we have detected so far is consistent with being a black hole. None of them require a Gravastar explanation, but none of them rule Gravastars out either. The observations fit both pictures. And as long as that remains true, the possibility lingers. Somewhere out there, mixed in with the black holes we have catalogued, there might be Gravastars. Objects born in the same violent collapse but stabilized by exotic matter instead of crushed into singularities. Objects that avoided the information paradox by avoiding the event horizon. Objects that sit at the boundary of what general relativity predicts and what quantum field theory allows. The name is memorable. Gravastar. It sounds like something out of science fiction, but the physics behind it is sober, careful, grounded in the equations of general relativity and quantum field theory. The idea is not a fantasy, it is a hypothesis, a testable hypothesis, at least in principle. We just do not have the tools to test it yet. And until we do, Gravastars will remain in that frustrating category of things that might be real but probably are not, but cannot quite be ruled out. They sit in the gap between what we know and what we can measure, and that gap, as it turns out, is exactly where the most interesting physics hides. Because if Gravastars are real, if collapsing stars can avoid singularities by flooding their cores with exotic matter, then the universe has been building something stranger than black holes, something with structure, with layers, with mechanisms we do not fully understand. Something held together by tension and negative pressure and vacuum energy. Something that looks like a predator but is built like a trap. And the next question, the one that leads directly into what comes next, is simple. What is this exotic matter actually made of? Where does it come from? And what happens to spacetime when you try to fill it with something that has negative pressure? So what exactly is this exotic matter that supposedly holds a Gravastar together? And why should the word exotic make you uncomfortable? Because in physics, exotic does not mean interesting or rare or imported from another galaxy. Exotic means rule-breaking. Exotic means the matter behaves in ways that violate the assumptions we normally make about how stuff works. And when you start breaking those assumptions, when you start allowing matter to do things that ordinary matter cannot do, you open a door that leads to some of the strangest, most unsettling predictions in all of theoretical physics. Time dilation so extreme that clocks nearly stop. Gravitational effects that push instead of pull. And space-time warped so severely that the geometry itself starts to look less like a smooth fabric and more like something on the edge of tearing apart. Let's start with the basics. What is matter supposed to do? Normal matter, the kind that makes up you and me and every star and planet we have ever observed, has positive energy density. That means if you measure how much energy sits in a given volume of space, you get a positive number. Normal matter also has positive pressure, or at worst, zero pressure. Solids and liquids push outward when compressed. Gases push outward even without compression. Radiation, light and photons, has pressure too, positive pressure. Even a vacuum, true empty space with no particles in it, has zero pressure. It does not push, it does not pull, it just sits there. That is normal. That is what the universe does everywhere we have looked. Exotic matter breaks that pattern. The technical definition, the one you find in papers on general relativity, is that exotic matter violates one or more of the energy conditions. Energy conditions are mathematical statements about the relationship between energy density and pressure that normal matter obeys. The weak energy condition says that energy density must be non-negative in every reference frame. You cannot have a region of space where the energy density is negative when measured by any observer. The strong energy condition says that energy density plus pressure must be non-negative. The dominant energy condition says that energy cannot flow faster than light. Every substance we have ever tested obeys these conditions. Water obeys them, steel obeys them, neutron star material obeys them. Even the quantum vacuum, with its virtual particles popping in and out of existence, obeys them on average. Exotic matter does not. In the context of a Gravastar, exotic matter specifically means matter with negative pressure, not zero pressure, not small pressure, negative, pressure that pulls inward instead of pushing outward, or more precisely, pressure that creates a tension like a stretched rubber band, pulling the space around it in ways that ordinary matter cannot. And here is where things get strange, because in general relativity, Pressure does not just affect the mechanical behavior of a substance, it affects gravity. Positive pressure adds to the gravitational pull. Negative pressure subtracts from it. If the negative pressure is strong enough, it can create a repulsive gravitational effect, gravity that pushes instead of pulls. That is not science fiction. That is what the Einstein field equations predict when you plug in matter with negative pressure. The Gravastar uses this. The core, the interior region sealed inside the shell, is modeled as having an equation of state where pressure equals negative energy density. Write that out in words. The pressure is exactly equal in magnitude to the energy density, but opposite in sign. If the energy density is positive, the pressure is negative. If you try to compress the core, the negative pressure pushes back, hard. The repulsive gravitational effect counteracts the inward pull of the mass, preventing the core from collapsing into a singularity. The core does not shrink to zero size because the negative pressure holds it open. The result is a region of spacetime that is extraordinarily dense but finite in extent. No singularity, no point of infinite density, just a core filled with exotic matter sitting at the edge of what general relativity allows. That equation of state, pressure equals negative energy density, should sound familiar. It is the same equation of state used to describe dark energy, the mysterious substance that is currently accelerating the expansion of the universe. We do not know what dark energy is. We have never isolated it in a lab. We have never measured its properties directly. But we know it is there because the universe is expanding faster every year, and the only way to explain that acceleration within general relativity is to invoke something with negative pressure. Cosmologists call it the cosmological constant. Einstein introduced it in 1917 to allow for a static universe, then abandoned it when Hubble discovered that the universe is expanding. Decades later, observations of distant supernovae in the late 1990s forced physicists to bring the cosmological constant back. The universe is not just expanding, it is accelerating. And the simplest explanation is that space itself has a small positive energy density and a negative pressure. Dark energy, exotic matter on the largest possible scale. The Gravastar hypothesis takes that same exotic matter and concentrates it. Instead of spreading thinly across the entire universe, dark energy gets packed into a ball 20 or 30 kilometers across. The core of a Gravastar is essentially a bubble of dark energy, sealed inside a shell of ultra-relativistic matter, sitting at the center of a collapsed stellar remnant. If that sounds implausible, you are not alone. Most physicists are skeptical. The objection is straightforward. We have no evidence that dark energy can exist in concentrated form. The dark energy we observe in the universe has an energy density of about 1 joule per cubic kilometer. That is almost nothing. A grain of sand contains more energy, and yet that tiny energy density, spread across billions of light years, is enough to accelerate the expansion of the entire cosmos. Now imagine taking that same stuff and compressing it until the energy density is a trillion times higher. Can you even do that? Does dark energy stay stable under those conditions, or does it undergo a phase transition into something else? Nobody knows. The equations allow it. Nature might not. Some Gravastar models use a more general form of exotic matter called quintessence. Quintessence is a hypothetical field with an equation of state somewhere between pressure equals negative energy density and pressure equals zero. The exact relationship depends on a parameter, usually called W. If W equals -1, you get dark energy. If W is between -1 and 0, you get quintessence. Quintessence behaves like dark energy, but with slightly different properties. It can vary in strength over time. It can cluster in ways that dark energy cannot. And some theoretical models suggest that quintessence could exist in the cores of compact objects, providing the negative pressure needed to stabilize a gravastar without requiring a full-on cosmological constant. The math is more flexible, the physics is just as speculative. Now let's talk about the shell, the thin layer separating the exotic core from the exterior vacuum. In the original Mazur-Mottola model, the shell has an equation of state where pressure equals energy density. That is not exotic in the same way the core is. Pressure equals energy density is the equation of state for ultra-relativistic matter. Matter moving so close to the speed of light that its kinetic energy dominates over its rest mass. Photons have this equation of state, so do neutrinos at very high energies. The shell is not made of photons or neutrinos. It is made of something denser, something under enormous tension, but with the same mathematical relationship between pressure and energy. The shell is stretched tight, holding the interior in and keeping the exterior out. And here is the critical part. The shell has surface tension, real mechanical tension, like a soap bubble or a drumhead. That tension is what stabilizes the entire structure. More recent models complicate the picture. Some papers describe the shell as having negative surface energy density and positive surface pressure. Negative surface energy density means that if you add up all the energy contained in the shell and divide by the shell's surface area, you get a negative number. That is deeply strange. It means the shell, in some sense, has less energy than empty space. And yet the shell also has positive pressure, pushing outward against the core and outward against the exterior. The combination negative energy with positive pressure is exactly the kind of exotic behavior that makes physicists nervous. It is mathematically allowed. General relativity does not forbid it. But we have never seen anything like it in nature. The shell is doing work that no known material can do. Why does any of this matter? Because the shell is not just a boundary, it is the mechanism that prevents the Gravastar from collapsing. In a black hole, there is no shell. The collapsing matter falls straight through to the singularity. Nothing stops it. In a neutron star, degeneracy pressure stops the collapse. The quantum mechanical resistance of neutrons packed together holds the star up. In a gravastar, the exotic matter in the core pushes outward, and the shell translates that push into mechanical tension. The tension resists compression. If you try to squeeze the gravastar, the shell pushes back. The restoring force is proportional to the tension. High tension means high resistance. The Gravastar sits in a state of equilibrium, balanced between the inward pull of gravity and the outward push of exotic matter. Remove the exotic matter and the equilibrium breaks. The shell collapses. The Gravastar becomes a black hole. That balance is delicate. Some stability analyses suggest that Gravastars can be stable against small perturbations. If you nudge the shell slightly, it oscillates and then settles back into equilibrium. Other analyses suggest that the stability depends critically on the exact properties of the exotic matter. Get the equation of state slightly wrong, and the Gravastar becomes unstable. It either collapses or explodes. The window of stability, if it exists, is narrow. And we have no way to test whether real exotic matter, if it exists, falls inside that window. We are guessing, educated guessing, constrained by the math, but guessing nonetheless. Now we get to the part that sounds like science fiction, but is rooted in the equations of general relativity. Time dilation. Black holes are famous for it. Fall toward a black hole and your watch ticks slower compared to a watch far away. The closer you get to the event horizon, the more extreme the effect becomes. At the horizon itself, time dilation becomes infinite. A clock sitting at the horizon, if such a thing could exist, would appear frozen to an outside observer. Time stops. Or more precisely, time continues for the infalling observer, but the mapping between the observer's time and the outside universe's time breaks down completely. Gravastars do not have event horizons, but they do have extreme space-time curvature. The shell sits very close to where the event horizon would have formed if the object were a black hole. The gravitational field near the shell is nearly as strong as the field near a black hole's horizon. That means time dilation near a Gravastar is almost as extreme. A clock on the surface of the shell, if you could place one there, would tick much slower than a clock far away. How much slower depends on the mass of the Gravastar and the radius of the shell. For a Gravastar with 10 solar masses and a shell radius of about 30 kilometers, the time dilation factor at the surface is enormous. A year on the shell might correspond to decades or centuries in the outside universe. Not infinite, not frozen, but close. That is the standard prediction. What happens inside the shell is less clear. The core is filled with exotic matter. Spacetime inside the core is curved, but the curvature is different from the curvature outside. The exotic matter creates a repulsive gravitational effect, pushing spacetime outward instead of pulling it inward. Some models describe the interior geometry as de Sitter space, a solution to the Einstein equations with positive curvature and a cosmological constant. De Sitter space is the geometry you get when you have a universe filled with nothing but dark energy. It is the opposite of a black hole interior, where a black hole interior curves inward toward a singularity. De Sitter space curves outward, expanding like a miniature accelerating universe. Time in de Sitter space behaves strangely. There are event horizons, but they are horizons of a different kind. Horizons that separate regions of space that are accelerating away from each other, not regions where light cannot escape. An observer sitting inside the core of a Gravastar, if such an observer could exist, would experience time passing normally. Their clock would tick at a steady rate, but the relationship between their time and the time of an observer outside the shell would be distorted by the geometry in between. Some popularizations of Gravastar physics claim that time runs backward inside the core. That is not supported by the standard models. Time reversal, in the sense of clocks literally running in reverse, does not appear in the published literature on Gravastars. What does appear is extreme time dilation and unusual causal structure. The geometry inside the core is so different from the geometry outside that the usual notion of simultaneity breaks down. An event happening inside the core and an event happening outside the shell cannot be easily compared. Which one happened first depends on the path you take through spacetime to connect them. That is not time reversal. That is relativity, doing what relativity does when spacetime is heavily curved. But it is strange enough that the boundary between inside and outside starts to feel less like a surface and more like a barrier separating two different kinds of reality. Now we come to the phrase spacetime tears. That phrase shows up in popular accounts of Gravastars, and it needs to be handled carefully. Spacetime does not literally tear. There is no rip, no hole, no place where the geometry becomes discontinuous. The Gravastar is a solution to the Einstein equations, and solutions to those equations are smooth. The curvature can be large, the curvature can be extreme, but it is always finite. That is the entire point of the Gravastar. It avoids the singularity. It avoids the place where curvature becomes infinite and the equations break down. What the phrase spacetime tears is trying to capture is the idea that spacetime inside a Gravastar is warped so severely, curved so dramatically, that it behaves in ways that seem almost pathological. The geometry is on the edge of what general relativity allows. One small step further and you would have a singularity, but the Gravastar stops one step short. The curvature peaks at the shell and then drops off inside the core because the exotic matter is pushing outward. The result is a spacetime geometry that is maximally warped without being broken. Think of it this way. Take a piece of fabric, stretch it, keep stretching. The fabric gets thinner. The threads get tighter. You can see through it in places. You are approaching the point where the fabric would tear, but you stop just before it tears. The fabric is under enormous tension. It is deformed. It is barely holding together, but it has not ripped. That is what spacetime near the shell of a Gravastar is like, stretched to the limit, curved to the maximum degree that the geometry can sustain without collapsing into a singularity, and held in that state by the exotic matter, providing just enough outward pressure to keep everything balanced. The shell itself is where the most extreme warping happens. The curvature of spacetime changes discontinuously as you cross the shell, not because spacetime is broken there, because the matter content changes. Outside the shell, you have vacuum. Inside the shell, you have exotic matter. The Einstein equations say that matter curves spacetime. Change the matter and you change the curvature. At the boundary between two different kinds of matter, the curvature can change sharply. That sharp change is called a junction condition. The junction conditions for a Gravastar are well studied. Physicists have checked the math carefully to make sure the geometry on both sides of the shell matches up correctly. The curvature is continuous in the directions parallel to the shell. It jumps in the direction perpendicular to the shell. That jump is what creates the surface tension. The shell is a boundary layer where spacetime transitions from one geometry to another. And that transition is violent in the sense that the curvature changes dramatically over a very short distance. How short? The shell in the original Mazur-Mortola model is infinitesimally thin, a mathematical surface with zero thickness. More realistic models give the shell a finite thickness, but still very small compared to the radius of the Gravastar. A shell a few meters thick on an object 30 kilometers across. The ratio is similar to the thickness of a soap bubble compared to its diameter, except this bubble is made of matter under pressures and tensions that exceed anything inside a neutron star, and the bubble is wrapped around a core of exotic matter that is pushing outward with a force strong enough to counteract the gravity of 10 suns. Here is what makes the shell terrifying. It is fragile, not in the sense that you could poke a hole in it with your finger. You could not get close enough to try. The tidal forces would destroy you, but fragile in the sense that the balance holding it together is precarious. The shell is under tension, enormous tension. If anything disrupts that tension, if the exotic matter in the core fluctuates, or if the shell gets hit by a high-energy particle, or if a gravitational wave passes through and jiggles the geometry, the shell could fail. And if the shell fails, the Gravastar has nothing left to stop the collapse. The exotic core would lose its containment, the outward pressure would vanish, gravity would win, the object would collapse into a black hole in less than a millisecond. From stable object to singularity faster than you can blink. That possibility, that a Gravastar could be sitting quietly for millions of years and then suddenly collapse, adds a layer of unpredictability that black holes do not have. A black hole, once formed, is eternal. It evaporates eventually, but that takes an unimaginable amount of time. A Gravastar, if it is real, might not be eternal. It might be metastable. Stable enough to last a long time, but vulnerable to the right kind of disturbance. Some researchers have compared the Gravastar's exotic matter to concepts in condensed matter physics. A vacuum condensate is a state where the quantum vacuum undergoes a phase transition, similar to how a gas condenses into a liquid or a metal becomes a superconductor. In a superconductor, electrons pair up and move through the material without resistance. The state has lower energy than the normal metallic state, and it is stable as long as the temperature stays low. Raise the temperature and the superconductor transitions back to a normal metal. The vacuum inside a Gravastar, in this analogy, is a condensed phase. It has different properties from the normal vacuum. Lower energy density, or possibly negative energy density, and negative pressure. The condensed vacuum is stable under the extreme conditions inside the collapsing core, but those conditions are fragile. Change the temperature or the density or the curvature and the vacuum could transition back to its normal state. If that happens, the exotic matter vanishes. The core becomes ordinary vacuum. The pressure goes to zero and the Gravastar collapses. Is any of this real? That is the question hanging over the entire discussion. Exotic matter with negative pressure is theoretically allowed. General relativity does not forbid it. Quantum field theory, in certain contexts, predicts effects that look like negative energy density. The Casimir effect, for example. Place two uncharged metal plates very close together in a vacuum and they attract each other. The attraction comes from a reduction in the vacuum energy between the plates compared to the vacuum energy outside. The space between the plates has negative energy density relative to the surrounding space. The effect is real. It has been measured in labs, but the energy density is tiny, far too small to hold up a collapsing stellar core. Scaling the Casimir effect up to Gravastar densities would require conditions we cannot create and may not even be possible. Dark energy is another candidate. We know dark energy exists on cosmological scales. We see its effects in the acceleration of the universe, but we do not know if dark energy can clump. The simplest models of dark energy, the cosmological constant, treat it as a property of spacetime itself, uniform everywhere. The same energy density in every cubic meter of space, from here to the edge of the observable universe. If dark energy is truly uniform, it cannot concentrate inside a Gravastar. It just sits there, filling all of space equally, irrelevant to the dynamics of compact objects. But if dark energy is a field, something dynamic that can vary from place to place, then maybe it can clump. Maybe under the right conditions, it can pile up inside a collapsing core and create the negative pressure needed to stop the collapse. That is speculative. No observation supports it. No experiment tests it. It is a maybe built on top of another maybe. The phrase exotic matter sounds almost benign, exotic, unusual, interesting, but the reality is harsher. Exotic matter, in the context of Gravastars, is matter that behaves in ways no confirmed substance behaves. It has properties we have never measured. It exerts forces we have never directly observed. It stabilizes objects we have never definitively detected. The entire Gravastar hypothesis rests on the existence of this matter. And if the matter does not exist, the hypothesis collapses. Not because the math is wrong, the math is fine. Because the physics requires an ingredient that nature may not provide. That uncertainty is where we are. Gravastars are mathematically consistent. They solve the equations. They avoid singularities. They provide a potential resolution to the information paradox. And they do it all using exotic matter with properties that sit right at the edge of what general relativity allows. But allowed is not the same as real. The universe does not care about mathematical consistency. It cares about what actually happens when a massive star collapses, and whether that collapse can be stopped by a phase transition in the vacuum or by exotic matter flooding the core. is a question we cannot yet answer. The door is open, the possibility is there. But we are standing on the threshold, staring into the dark, trying to decide whether the thing we are looking at is a black hole or something stranger. And the decision matters because if Gravastars are real, if they exist out there in the numbers that black holes do, then the universe is filled with objects held together by forces we do not understand, stabilized by matter we have never confirmed, sitting on the edge of collapse every moment they exist. Bombs made of exotic matter and surface tension, ticking quietly in the dark, waiting. We have been talking about Gravastars as objects that form from the collapse of massive stars, cores weighing 10, 20, maybe 50 times the mass of the Sun, collapsing under their own gravity and stabilizing at the last possible moment before an event horizon forms. Those are stellar mass Gravastars, if they exist. Compact objects you could hold, hypothetically, in a volume the size of a small city. Objects measured in kilometers. But the Gravastar hypothesis does not stop there. The mathematics that allows a stellar remnant to stabilize with exotic matter does not care about the mass scale. The equations work just as well for 10 solar masses as they do for 1,000,000 or 1,000,000,000. And if Gravastars can exist at stellar mass scales, then there is no obvious reason they could not exist at the other end of the spectrum, at the centers of galaxies, in the places where we currently think supermassive black holes live. Objects weighing not 10 or 50 times the Sun's mass, but 1,000,000 times, 10 million, 1,000,000,000, supermassive Gravastars. And if those exist, then the scale of the horror changes completely. Start with the mass, 1,000,000 solar masses. Write that out in kilograms, and you get a number with 36 digits. 2 times 10 to the 36 kilograms. That is not a number the human brain is equipped to process. So let me give you something to anchor it. Our Sun weighs about 2 times 10 to the 30 kilograms, 1 solar mass. The Sun contains 99.86% of all the mass in the solar system. Every planet, every asteroid, every comet, every speck of dust orbiting out past Neptune, all of it combined makes up less than 0.2% of the total. The Sun is everything. Now take 1,000,000 suns, stack them together, compress them down. You have 1,000,000 solar masses. That is the scale we are talking about. For context, the supermassive black hole at the center of our Milky Way galaxy, Sagittarius A star, weighs about 4,000,000 solar masses. The black hole at the center of the galaxy Messier 87, the one imaged by the Event Horizon Telescope in 2019, weighs about 6.5 billion solar masses. Supermassive black holes are common. Most large galaxies have one sitting at their center. The masses range from hundreds of thousands of solar masses on the low end to tens of billions on the high end. 1,000,000 solar mass object is on the smaller side of the supermassive scale. Not a giant, but far, far larger than anything that could form from a single collapsing star. Stellar collapse tops out at maybe 100 solar masses if you are generous. To build something 1,000,000 times heavier, you need a different process. You need accretion. Gas falling inward over millions of years, feeding the central object, adding mass layer by layer. Or you need mergers. Smaller black holes colliding and combining, building up mass through repeated collisions. Either way, the process takes time. Supermassive black holes did not form overnight. They grew. If supermassive Gravastars exist, they would have grown the same way. Start with a seed, maybe a stellar mass Gravastar formed in the early universe from the collapse of one of the first generation of stars. The seed sits at the center of a young galaxy, surrounded by gas. The gas falls inward, pulled by gravity, and lands on the shell. The shell absorbs the mass. the Gravastar grows. Over millions of years, the object accumulates more and more material, swelling in size and mass until it weighs millions of times what it started with. The process would look identical to the growth of a supermassive black hole. From the outside, you could not tell the difference. The gravitational field is the same. The accretion disk is the same. The jets of radiation shooting out from the poles, powered by magnetic fields tangled in the infalling gas, would look the same. The only difference would be inside. No event horizon, no singularity, just a shell of exotic matter holding the structure together. Now let's talk about size. The radius of a Gravastar is tied to its mass. The more massive the Gravastar, the larger its radius. For a black hole, the event horizon radius is given by the Schwarzschild radius, 2 times the gravitational constant times the mass, divided by the speed of light squared. For 1 solar mass, that gives you about 3 kilometers. For 1 million solar masses, scale it up, 3 million kilometers. That is roughly twice the distance from the Earth to the Sun, a sphere twice as wide as an astronomical unit. A black hole with 1 million solar masses would have an event horizon stretching across a volume you could fit the Earth's entire orbit inside, twice over. A Gravastar with the same mass would be slightly larger. The shell sits just outside where the event horizon would form. The models describe Gravastars as having a radius greater than or approximately equal to 2 times the mass in geometric units, meaning the shell is perched right at the edge of the Schwarzschild radius or just barely beyond it. The exact radius depends on the details of the model, the properties of the exotic matter, the thickness of the shell. But the key point is that a supermassive Gravastar is almost as compact as a supermassive black hole. Almost. The difference is small, a few percent, maybe less. From a distance of a few light years, you would not notice. The object would still be dark. It would still warp spacetime severely enough to lens light into rings. Stars orbiting nearby would still move at absurd velocities, whipping around the central mass at thousands of kilometers per second. The Gravastar would be a monster, just a different kind of monster. Let me put the size in perspective. 3 million kilometers. Light takes about 10 seconds to cross that distance. For comparison, light takes about 1 second to travel from the Earth to the Moon. 1 million solar mass Gravastar would have a shell 10 light seconds across. If you could somehow stand at the center of the shell and shine a flashlight outward, the light would take 5 seconds to reach the edge. That sounds fast until you realize that 5 seconds is an eternity when you are talking about an object held together by surface tension. The shell is under constant stress. Gravity is pulling inward. The exotic core is pushing outward. The balance is delicate. Any fluctuation, any ripple traveling through the shell would take seconds to propagate from one side to the other. The shell is not rigid. It is flexible. It can oscillate, and if it oscillates too much, it could fail. Now let's address the thin shell paradox. The phrase comes from the structure of the Gravastar itself. The object has 3 regions: an exterior vacuum, a thin shell, and an exotic interior. The shell, despite being described as thin, contains an enormous amount of mass. In the models, the shell's mass is written as 4 times pi times the radius squared times the surface density. Surface density, mass per unit area, not mass per unit volume. The shell is so thin compared to the radius of the Gravastar that you measure its density in terms of how much mass sits on a given patch of the surface, not how much fills a given volume of space. The shell is essentially a 2-dimensional object embedded in 3-dimensional space, a membrane, a boundary layer. And, despite being thin, it holds most of the Gravastar's mass. Here is where the numbers get uncomfortable. Take a 1,000,000 solar mass Gravastar with a shell radius of 3 million kilometers. The surface area of a sphere is 4 times pi times the radius squared. Plug in the radius and you get about 2.8 times 10 to the 20 square meters. That is the area of the shell. Now take 1,000,000 solar masses, about 2 times 10 to the 36 kilograms, and spread it over that area. You get a surface density of roughly 7 times 10 to the 15 kilograms per square meter, 7 million billion kilograms per square meter. For comparison, a sheet of steel 1 meter thick has a surface density of about 8,000 kilograms per square meter. The shell of a 1,000,000 solar mass Gravastar is about 1 trillion times denser than solid steel, and that is the surface density. The actual density, mass per unit volume, depends on the thickness of the shell. If the shell is a few hundred meters thick, which is thin compared to a radius of 3 million kilometers, the volume density would be even higher, approaching or exceeding the density of a neutron star, maybe surpassing it. The paradox is this: how do you pack 1,000,000 solar masses into a shell that is, by the standards of the object's overall size, vanishingly thin? The shell is not spread out like the atmosphere of a planet. It is concentrated, compressed. Every cubic meter of the shell contains more mass than a cubic meter of neutron star material, and yet the shell is stable. It is not collapsing. It is not exploding. It is sitting there, balanced on the edge between those two outcomes, held together by tension, surface tension, the same force that holds a soap bubble together, scaled up to a level that makes neutron degeneracy pressure look gentle. The models treat the shell as having finite thickness, but in some simplified versions, the thickness goes to 0, an infinitely thin shell, a mathematical surface with no volume. That cannot be physically real. You cannot have 0 thickness and non-zero mass. The mass has to be somewhere. But the infinitely thin shell is a useful approximation because it simplifies the equations. And the fact that the approximation works, that you can solve the Einstein equations with an infinitely thin shell and get sensible answers, tells you something. It tells you that the shell can be arbitrarily thin as long as the surface density is high enough. The thinner the shell, the higher the density. The limit, as thickness goes to 0, is a shell with infinite density. That is not physical. But the fact that you can approach that limit and still have a stable solution suggests that the Gravastar is living on the edge. A structure balanced so precisely that even the slightest deviation would push it over. Now think about what happens if that shell fails. 1,000,000 solar masses, compressed into a membrane a few hundred meters thick, suddenly loses its structural support. The exotic core stops pushing outward. The tension vanishes, gravity wins. The shell collapses inward at a significant fraction of the speed of light. In less than a second, the entire structure implodes. 1,000,000 solar masses falling inward, converting gravitational potential energy into kinetic energy. The amount of energy released would be staggering. Take the mass, multiply by the speed of light squared, and you get the total rest energy. For 1,000,000 solar masses, that is about 2 times 10 to the 53 joules. Not all of that gets released in the collapse. Most of it stays locked in the mass of the object. But even a small fraction, 1%, 1/10 of a percent, is still an unimaginable amount of energy. 10 to the 50 joules. That is the energy output of a large supernova. Released not over weeks or months, but in a fraction of a second. The collapse of 1,000,000 solar mass Gravastar, if it happened, would be one of the most violent events in the universe. Compare that to a black hole. A supermassive black hole with the same mass is stable, eternally stable. Once formed, it just sits there. It grows if it accretes matter. It evaporates on timescales so long that they are meaningless, trillions of years, but it does not collapse. It cannot collapse. It is already as collapsed as anything can be. The singularity at the center is already at zero volume. There is nowhere left to go. A Gravastar, by contrast, is a metastable object, stable for now, stable as long as the exotic matter in the core behaves, stable as long as nothing disturbs the shell, but vulnerable. One good kick and the whole thing comes down. What could kick it? A gravitational wave passing through. Gravitational waves are ripples in space-time itself, traveling at the speed of light, stretching and compressing everything in their path. A strong enough wave could jostle the shell, setting up oscillations that grow until the shell tears, or another compact object falling in. A smaller Gravastar, or a black hole, or a neutron star, spiraling inward, colliding with the shell, punching through. The collision would dump enormous amounts of energy into the shell in a very short time. The shell might absorb it, or it might not, or simple accretion. Gas falling onto the shell, piling up, adding mass. If the mass accumulates faster than the exotic core can adjust, the balance shifts. The shell gets heavier, gravity gets stronger, the tension in the shell increases. At some point, the tension exceeds what the shell can handle. It snaps. The Gravastar collapses. The comparison to a neutron star is worth making explicit. A neutron star with 2 solar masses has a radius of about 12 kilometers. The density is roughly 5 times 10 to the 17 kilograms per cubic meter. A sugar cube of neutron star material weighs about 1 billion tons. That density is already beyond anything we can create or even properly simulate on Earth. Now consider a 1 million solar mass Gravastar. If the shell is a few hundred meters thick and has a radius of 3 million kilometers, the average density of the shell, mass divided by volume, is comparable to or greater than the density of a neutron star. But the shell is not held up by degeneracy pressure. It is held up by tension, mechanical tension, like a cable supporting a bridge. Except the cable is wrapped around an exotic core, pushing outward with the equivalent pressure of dark energy. The density inside the core is different. The core is not made of matter in the traditional sense. It is a vacuum condensate, exotic vacuum. The energy density could be positive, negative, or close to zero, depending on the model. But the pressure is negative. That negative pressure is what creates the repulsive gravitational effect, and the magnitude of the pressure determines how much the core pushes outward. For a 1 million solar mass Gravastar, the pressure inside the core would have to be enormous, enough to counteract the inward pull of 1 million suns. In geometric units, pressure contributes to the stress-energy tensor the same way mass does. High pressure means strong gravitational effects. Negative pressure means repulsive gravitational effects. The core of a supermassive Gravastar would be pushing outward with a force that ordinary matter cannot match. Now let's think about what it would look like to approach one of these objects. You are in a spaceship falling toward a 1 million solar mass Gravastar sitting at the center of a galaxy. From a distance, it looks like a supermassive black hole. There is an accretion disk, a swirling disk of gas glowing brightly as it spirals inward. The disk is hot, millions of degrees. It emits X-rays and ultraviolet light, lighting up the surrounding region. Jets of plasma shoot out from the poles, driven by magnetic fields twisted by the rotation of the disk. The jets stretch for thousands of light years, carving cavities in the intergalactic medium. This is the familiar picture: active galactic nucleus, quasar, blazar. The terminology changes depending on the viewing angle, but the basic structure is the same. a supermassive compact object surrounded by an accretion disk. From here, you cannot tell whether the object is a black hole or a gravastar. They look identical. You fall closer, the gravitational pull strengthens, your ship accelerates. The stars behind you redshift as you fall deeper into the gravitational well. The stars ahead blueshift, the sky distorts. Light from distant galaxies bends around the central mass, forming rings and arcs. Einstein rings, gravitational lensing. Still, nothing tells you whether the object is a black hole or a gravastar. The lensing depends only on the mass and the distance. Both objects have the same mass. Both warp spacetime the same way. You fall even closer. Now you are within a few light minutes of the shell. The tidal forces start to become noticeable. The difference in gravitational pull between the front of your ship and the back is growing. For a million solar mass object, the tidal forces at the shell are much weaker than the tidal forces at the horizon of a stellar mass black hole. The shell is so far from the center of mass that the curvature of spacetime, while extreme, is relatively gentle. You would not be torn apart. Not yet. But your instruments would start detecting something strange. If the Gravastar has a shell, and if that shell is oscillating or emitting radiation or interacting with the accretion disk in any unusual way, you might see deviations from the black hole prediction. Small deviations, subtle but measurable if you know what to look for. You fall closer still. Now you are approaching the shell itself. If this were a black hole, you would be about to cross the event horizon. Time dilation would be extreme. Your clocks would be ticking much slower than clocks far away. Signals you send back to your home galaxy would take longer and longer to arrive, stretched out by the curvature of spacetime. And once you crossed the horizon, there would be no coming back. Every path would lead inward. But this is not a black hole. This is a gravastar, and the shell is a physical surface. You hit it. What happens next depends on the properties of the shell. In some models, the shell is rigid. You crash into it like hitting a wall. The collision would be catastrophic. The kinetic energy of your ship, built up over the long fall inward, gets dumped into the shell in an instant. Your ship vaporizes. The shell absorbs the energy, heats up slightly, and continues sitting there. In other models, the shell is more like a fluid. You would sink into it, slowed by friction and pressure, your ship torn apart by the stresses as you penetrate deeper into the shell. Either way, you do not survive, but you also do not fall into a singularity. There is no singularity. The shell stops you. Beyond the shell is the exotic core, a region of spacetime filled with vacuum energy, negative pressure, repulsive gravity. You cannot reach it. The shell is the boundary. And the boundary is impenetrable, not because of an event horizon, but because of the sheer density and tension of the matter making up the shell. That distinction matters. A black hole traps you with geometry. Once you cross the horizon, spacetime itself prevents you from leaving. A gravastar traps you with matter. The shell is a physical barrier. It is not that you cannot leave, it is that you cannot get through. The shell is so dense, under so much tension, that nothing short of another compact object could penetrate it. And even then, the collision would probably destroy both objects. A gravastar is not a prison made of spacetime. It is a fortress made of exotic matter. The difference is subtle from the outside. From the inside, the difference is everything. The implications of a million solar mass object without an event horizon are profound. Black holes hide information behind the horizon. Everything that falls in, all the details about the particles, the quantum states, the arrangement of atoms, vanishes from the perspective of the outside universe. The information is either destroyed, which violates quantum mechanics, or it is encoded somehow on the horizon or in the Hawking radiation, which leads to paradoxes we have not resolved. A Gravastar does not have an event horizon. Information that falls onto the shell does not vanish. It gets absorbed by the shell. The shell heats up. The energy spreads out across the surface. The information, in principle, is still there, encoded in the thermal state of the shell. Scrambled, yes. Unreadable, probably, but not destroyed. The Gravastar provides a way out of the information paradox by refusing to form the structure, the event horizon, that causes the paradox in the first place. That is elegant, almost too elegant. It solves the problem by denying the problem exists, and it raises new questions. How does the shell store information? How much information can it hold? What happens if the shell reaches some kind of maximum entropy and cannot absorb any more? Does it radiate the information back out? Does it undergo a phase transition and turn into something else? The Gravastar hypothesis answers one question and opens a dozen more. The gravitational influence of a supermassive Gravastar would extend across the entire galaxy. Stars near the galactic center would orbit the Gravastar at high speeds. We see this around Sagittarius A star. Stars in tight orbits, some completing a full loop in less than 20 years, moving at several % of the speed of light. Those orbits tell us the mass of the central object, 4 million solar masses, but they do not tell us what kind of object it is. A black hole or a Gravastar would produce the same orbits. The gravitational field outside the object is determined entirely by the mass. The internal structure is invisible, hidden behind the shell or behind the horizon. Either way, we cannot see it, but there might be clues. If the shell is oscillating, if it is ringing like a bell in response to infalling matter or passing gravitational waves, those oscillations would produce a characteristic signal, gravitational waves with specific frequencies. The frequencies would depend on the mass of the Gravastar, the radius of the shell, and the properties of the exotic matter. They would not match the frequencies predicted for a black hole. Black holes also ring when disturbed. The ring-down signal, the gravitational waves emitted as a black hole settles into a stable state after a merger or a collision, has a well-defined frequency and damping time. If Gravastars exist, their ring-down signals would be different, slightly different. Maybe not enough to distinguish them with current detectors, but enough that future detectors, more sensitive, more precise, might be able to tell. That is the hope. The possibility that we could detect a supermassive Gravastar not by seeing it directly, but by listening to the gravitational waves it produces and noticing that the waves do not quite match the black hole template. The scale of these objects is almost impossible to grasp. 1 million solar masses. A shell 3 million kilometers across. A surface density trillions of times higher than steel. A core filled with exotic matter pushing outward with the force of dark energy. An object balanced on the edge of collapse, held together by tension, sitting at the center of a galaxy, feeding on gas and stars, growing larger and heavier with every passing million years. And if the hypothesis is correct, if Gravastars can exist at supermassive scales, then every supermassive black hole we have ever observed might not be a black hole. It might be a Gravastar, a monster wearing a mask. And we would have no way to know unless we could get close enough to measure the differences, or unless one of them collapsed. And if 1 million solar mass Gravastar collapsed, if the shell failed and the structure imploded, the energy release would light up half the universe. A burst of gravitational waves strong enough to shake spacetime across billions of light years. A flash of radiation as the shell vaporized. And then silence. A new black hole born from the death of something even stranger. That is the scale of Gravastar horror. Not the horror of inevitability, the way a black hole is inevitable once the collapse begins. The horror of fragility. An object so massive, so dense, so powerful, and yet so delicate that one wrong move could bring the whole thing down. A cosmic tightrope walker made of exotic matter and tension. And the wire is fraying. We have been building up to this for thousands of words. A gravastar is allowed by the mathematics. The structure is consistent with general relativity. The equations work. And yet, every time a physicist sits down to actually calculate what a gravastar would do, what it would look like during formation, how it would behave when you disturb it, they run into walls. Not small walls, not minor inconveniences. Mathematical walls so high that decades of effort have barely made a dent. The Gravastar hypothesis is elegant on paper. In practice, it is a nightmare. A beautiful, seductive nightmare that refuses to resolve itself into something you can confidently call real or definitively rule out as impossible. And the reason it is a nightmare is that the mathematics required to describe it sits at the intersection of three frameworks that do not play well together: general relativity, quantum field theory, and thermodynamics. Get all three to agree, and you might have a Gravastar. Get even one of them wrong, and the whole structure collapses. Let's start with the Einstein field equations, because that is where everything in general relativity starts. The equations are deceptively simple to write down in words. The curvature of spacetime is proportional to the energy and momentum of whatever matter and energy are present. Curvature on one side, stress energy on the other. The two are linked by a constant, the gravitational constant, divided by the speed of light to the fourth power. That constant is tiny, which is why it takes enormous amounts of energy to produce noticeable spacetime curvature. But the equations themselves are not simple. They are a set of 10 coupled nonlinear partial differential equations. 10 equations because spacetime has 4 dimensions and the curvature tensor has 10 independent components. Coupled because the equations are not independent. Solving one affects the others. Nonlinear because the equations contain terms where the curvature multiplies itself. And partial differential equations because they describe how things change across space and time. Solving the Einstein equations exactly is hard. Solving them for a realistic physical system is often impossible. Physicists spend entire careers finding approximate solutions or numerical solutions or solutions that work only under very specific symmetries. The Schwarzschild solution, the one that describes a non-rotating black hole, is one of the few exact solutions that is simple enough to write down in a form anyone can work with. Carl Schwarzschild found it in 1916, less than a year after Einstein published the field equations. The solution assumes spherical symmetry, no rotation, no electric charge, no magnetic field, just a point mass sitting at the center and space-time curving around it. The Schwarzschild solution has an event horizon, the radius where the geometry becomes so warped that light cannot escape. And inside the horizon, the solution predicts a singularity, a place where the curvature becomes infinite and the equations stop working. The singularity is a feature of the Schwarzschild solution, not a bug, not an approximation, a direct prediction of the math. If you have spherical symmetry and you compress enough mass into a small enough region, you get a singularity. That is what the Einstein equations say. The Gravastar is also a solution to the Einstein equations. But it is not the Schwarzschild solution, it is a different solution. A solution where the interior is not empty vacuum falling toward a singularity, but filled with exotic matter pushing outward. The Gravastar replaces the singularity with a region of exotic vacuum, replaces the event horizon with a physical shell. And the question that has been hanging over the Gravastar hypothesis since Mazur and Mottola introduced it in 2001 is simple. How do you get from the Schwarzschild solution to the Gravastar solution? If a massive star is collapsing and the collapse is following the Schwarzschild geometry, what mechanism makes it stop and turn into a Gravastar instead? What changes? What kicks in at the last moment to prevent the singularity from forming? The answer Mazur and Mottola proposed involves a phase transition in the vacuum, a quantum phase transition. The idea is that as the collapsing core approaches the conditions where an event horizon would form, the vacuum undergoes a shift. It transitions from its normal state into a different state, a state with negative pressure. The transition releases energy, or more precisely, it changes the energy density and pressure of the vacuum in a way that alters the stress-energy tensor. And because the Einstein equations link curvature to stress energy, changing the stress energy changes the curvature. The collapse stops, the geometry shifts. Instead of continuing to fall inward toward a singularity, the core stabilizes in a new configuration. A configuration with a de Sitter interior, a thin shell, and a Schwarzschild exterior, a Gravastar. That is the story. The problem is that the story requires a phase transition that we have never observed, and that current quantum field theory does not clearly predict. Phase transitions are common in condensed matter physics. Water freezes into ice, metals become superconductors. Magnets lose their magnetization above a certain temperature. Those transitions happen because the system reaches a critical point where one configuration becomes more stable than another. The molecules or atoms or electrons rearrange themselves into a lower energy state. But those are transitions in matter. The Gravastar hypothesis requires a transition in the vacuum itself, empty space rearranging itself into a different kind of empty space, a vacuum with different properties. And we do not have a well-developed theory of how that would work. Quantum field theory allows for multiple vacuum states in principle. The Higgs field, which gives mass to particles in the standard model of particle physics, has a vacuum expectation value, a non-zero value in its lowest energy state. If conditions were different, if the temperature were higher or the energy density were higher, the Higgs field could sit in a different state, a false vacuum, a state that looks stable but is not actually the lowest energy configuration. The universe could be sitting in a false vacuum right now, and we would not know it until a bubble of true vacuum nucleated somewhere and expanded at the speed of light, converting everything it touched into the lower energy state. That scenario, called vacuum decay, is one of the hypothetical ways the universe could end. Not comforting, but it shows that the idea of multiple vacuum states is not completely foreign to modern physics. It is just speculative. We have no experimental evidence that our vacuum is false. We have no evidence that any other vacuum state exists. The Gravastar hypothesis takes that speculative idea and pushes it further. It proposes that under the extreme conditions inside a collapsing stellar core, the vacuum can transition not just into a different state, but into a state with an equation of state like dark energy. Pressure equals negative energy density. And it proposes that this transition happens fast enough and thoroughly enough to halt the collapse before an event horizon forms. That is a lot of maybes stacked on top of each other. Maybe the vacuum has multiple states. Maybe one of those states has negative pressure. Maybe the transition can happen during gravitational collapse. Maybe the transition happens in the right place at the right time to stabilize the core. Every maybe is a place where the hypothesis could fail, and we do not have the tools to check any of them experimentally. We cannot recreate the conditions inside a collapsing stellar core. We cannot trigger a vacuum phase transition. We cannot even confirm that exotic matter with the required properties exists outside of the equations. Then there is the problem of the shell, the thin shell separating the interior from the exterior. In the original Mesur-Mottola model, the shell is a boundary layer with an equation of state where pressure equals energy density. That is the equation of state for ultra-relativistic matter. Matter moving at speeds very close to the speed of light. Photons have this equation of state. So do particles in a relativistic gas. But the shell of a Gravastar is not made of photons. It is made of something with mass, something under tension. And the tension has to be strong enough to hold the shell together against the combined pull of the mass inside and the mass of the shell itself. The tension is described mathematically as surface tension, the same concept that holds a soap bubble together. Except the soap bubble is wrapped around 1 million solar masses and the surface tension is strong enough to resist gravitational collapse. Surface tension in the context of a Gravastar is not a small effect. It is the dominant effect. The shell is under so much tension that even a small perturbation could set up oscillations. The shell could ring like a bell. Physicists have studied this. They have calculated the quasi-normal modes of Gravastars. Quasi-normal modes are the characteristic frequencies at which an object vibrates when disturbed. Every object has them. A drum has quasi-normal modes. A bell has quasi-normal modes. A black hole has quasi-normal modes. When a black hole is disturbed, say by a smaller black hole merging into it, the resulting object rings at specific frequencies as it settles into a stable state. The frequencies depend on the mass and spin of the black hole, nothing else. Black holes have no hair, no distinguishing features beyond mass, charge, and spin. The ringdown is the same for every black hole with the same mass. Gravastars are different. A paper published in 2007 by P. Cunha and collaborators calculated the quasi-normal modes of a Gravastar and compared them to the quasi-normal modes of a black hole with the same mass. The conclusion was clear. The modes differ, not by a huge amount, but enough that if you could measure the ringdown signal with sufficient precision, you could tell whether the object was a black hole or a Gravastar. That is the smoking gun, the observable signature, the thing that could, in principle, distinguish the two. The challenge is that the differences are subtle, buried in the fine details of the gravitational wave signal. Current detectors, LIGO and Virgo and Kagra, are sensitive enough to detect the ringdown from merging black holes, but they are not yet sensitive enough to resolve the small differences that would indicate a Gravastar. Future detectors might be the Einstein telescope, a proposed European gravitational wave observatory; Cosmic Explorer, a proposed upgrade to LIGO; the Laser Interferometer Space Antenna, LISA, which will observe gravitational waves from space. Those instruments might have the precision needed to test the Gravastar hypothesis directly. Might, not will. The detection depends on whether Gravastars exist, whether they merge often enough for us to observe, and whether the signal is clean enough to distinguish from noise. A lot of ifs. The boundary conditions are where the mathematics gets truly ugly. A Gravastar is not a single smooth geometry. It is 3 regions patched together. Each region has its own metric, its own description of how spacetime curves. The exterior is Schwarzschild spacetime. The shell is a thin layer with its own stress-energy tensor. The interior is de Sitter spacetime. At the boundaries between these regions, the metrics have to match. You cannot just glue 2 different spacetimes together and call it a day. The geometry has to be continuous. The derivatives of the geometry have to behave correctly. And the stress-energy tensor has to be consistent with the Einstein equations on both sides of the boundary. Those constraints are called junction conditions. Israel junction conditions, named after the physicist Werner Israel, who worked out the mathematics of thin shells in general relativity in the 1960s. The junction conditions impose strict requirements on what the shell can be made of. The surface density has to have a specific value. The surface pressure has to balance the curvature on both sides. Get the numbers wrong, and the geometry does not match. The solution is not consistent. You do not have a Gravastar. You have a mathematical error. A paper published in 2024 emphasized this point. The authors argued that many Gravastar models in the literature are not self-consistent solutions to the Einstein equations across the entire spacetime. They are patched solutions, approximate solutions, solutions that work in certain regions but fail when you check the junction conditions carefully. The paper called for physically viable Gravastars to be exact solutions, not approximations, not numerical fits. Exact. That is a high bar. Exact solutions to the Einstein equations are rare. Most physical systems are too complicated to solve exactly. You have to use approximations or numerical methods. Insisting on exact solutions limits the range of possible Gravastar models significantly, but the authors argued that anything less is not convincing. If the Gravastar is supposed to be a serious alternative to black holes, it needs to be a solution you can trust. A solution where every term in every equation is accounted for. No shortcuts, no hand-waving, just the math. Quantum gravity enters the picture because the Gravastar hypothesis relies on physics that classical general relativity does not fully capture. Vacuum phase transitions, exotic matter, negative energy densities, those are quantum effects. Classical general relativity treats spacetime as a smooth geometry. Quantum mechanics says that at very small scales, spacetime is not smooth, it is foamy, fluctuating. Virtual particles pop in and out of existence. The vacuum is not empty, it is full of quantum activity. And when you try to describe gravitational collapse at scales where quantum effects matter, classical general relativity breaks down. You need a theory that combines general relativity with quantum mechanics, a theory of quantum gravity. We do not have one, not a complete one, not one that makes testable predictions we can check. What we have are candidates: string theory, loop quantum gravity, causal set theory. Each one offers a different picture of what spacetime looks like at the Planck scale, and none of them are confirmed. Some Gravastar models try to incorporate quantum gravity effects explicitly. A paper published in 2021 described what the authors called a pure quantum Gravastar, a solution to the quantum improved Einstein equations. The quantum improved equations are a modification of the classical Einstein equations that include corrections from quantum effects. The corrections are small at large scales. They only matter when the curvature becomes very large or when you are very close to a singularity. The authors argued that when you include those corrections, the collapse can stop before a singularity forms. The quantum effects push back against the gravitational pull, stabilizing the core in a Gravastar configuration. The paper was careful to note that the solution was approximate. The quantum corrections were modeled using a specific framework, effective field theory, which may or may not capture the full behavior of quantum gravity. But the result was suggestive. It showed that quantum effects, if they behave the way the model predicts, could prevent singularity formation. Could, not do, could. The word choice is deliberate. The authors were not claiming Gravastars exist. They were claiming the mathematics allows them. Stability is the problem that keeps coming back. Even if you can construct a Gravastar on paper, even if the junction conditions match and the stress-energy tensor is consistent and the quantum corrections stabilize the interior, you still have to show that the object is stable, that it does not collapse into a black hole or explode or oscillate so violently that it tears itself apart. Stability analysis in general relativity is hard. You start with a static solution, a configuration that is not changing in time. Then you perturb it. Add a small amount of extra mass. Jiggle the shell, send a gravitational wave through, and you watch what happens. If the perturbations decay, if the object settles back into its original configuration, the solution is stable. If the perturbations grow, if small changes amplify over time, the solution is unstable. Unstable solutions do not last. They might form briefly during a collapse, but they would not survive long enough to be observed. A study published in 2007 analyzed the stability of Gravastars against axial perturbations. Axial perturbations are disturbances that twist the geometry without changing the overall shape, like giving the shell a sideways push. The study found that Gravastars can be stable against these perturbations under certain conditions. The conditions depend on the properties of the shell, the surface tension, the thickness, the equation of state. Get those parameters right, and the Gravastar settles back into equilibrium after being disturbed. Get them wrong, and the oscillations grow, the shell fails, the object collapses. The study did not test all possible perturbations. It focused on axial modes because those are mathematically simpler. Radial perturbations, where the shell expands and contracts, are harder to analyze. The jury is still out on whether Gravastars are stable against all possible disturbances. Some papers claim they are. Others argue that the stability window is so narrow that real Gravastars, if they formed, would be unlikely to survive. Then there is the formation problem. How do you make a Gravastar? The standard story says they form during the collapse of a massive star. The core exhausts its nuclear fuel. Fusion stops. Gravity takes over. The core collapses, and at some point during the collapse, a vacuum phase transition occurs. The exotic matter floods the core. The collapse halts. You end up with a Gravastar. That is the story, but the details are missing. At what point during the collapse does the phase transition happen? What triggers it? How long does it take? Does the transition happen uniformly throughout the core, or does it start in one place and spread outward? And most importantly, is there enough time for the transition to happen before an event horizon forms? If the collapse is too fast, if the core crosses the point of no return before the exotic matter can stabilize it, you get a black hole, not a Gravastar. The transition has to happen at exactly the right moment. Too early, and the core is not dense enough to trigger the transition. Too late, and the event horizon forms first. The timing is delicate, and we have no way to test whether nature gets the timing right. Some researchers have tried to model the formation process numerically. Take a collapsing core. Simulate the dynamics. Add in a phase transition at some critical density. Watch what happens. The simulations are difficult because you have to model both the classical dynamics of the collapsing matter and the quantum effects that drive the phase transition. The two operate on different scales and use different mathematical tools. Combining them in a way that is both accurate and computationally feasible is a challenge. The results so far are inconclusive. Some simulations suggest that Gravastar formation is possible. Others suggest that the collapse always overtakes the phase transition. The object forms a black hole before the exotic matter can stop it. The discrepancy probably comes from differences in how the phase transition is modeled, which equation of state you use, what assumptions you make about the exotic matter. The simulations are only as good as the input physics, and the input physics is speculative. The no-hair theorem is one of the most famous results in black hole physics. The theorem says that black holes are simple, completely characterized by three numbers: mass, electric charge, and angular momentum. Everything else, every detail about what fell into the black hole, every bit of information about the collapsing star or the infalling matter, erases itself. Black holes have no hair, no distinguishing features beyond those three parameters. Two black holes with the same mass, charge, and spin are identical. You cannot tell them apart by looking at their external gravitational field or their event horizon. They are the same object. The no-hair theorem is a consequence of general relativity. It follows from the Einstein equations and the assumption that the black hole has settled into a stationary state. The theorem has been tested extensively. Every black hole we have observed through gravitational waves or electromagnetic radiation or the orbits of nearby stars is consistent with the no-hair prediction. Black holes really do appear to be simple. Gravastars, if they exist, violate the no-hair theorem. Not in the sense that they break the mathematics, in the sense that they have internal structure. A shell with specific properties, a core with a specific equation of state. Two gravastars with the same mass and spin could have different internal configurations, different shell thicknesses, different amounts of exotic matter in the core, different surface tensions. Those differences would not be visible from far away. The external gravitational field would be the same, but the internal structure would differ. And that internal structure could, in principle, encode information. Information about how the Gravastar formed, what kind of star collapsed to create it, what happened during the collapse. That information would be locked inside the shell, inaccessible to outside observers, but still present, still part of the object's physical state. The Gravastar preserves information in a way that a black hole does not, or at least in a way that a black hole appears not to. The information paradox, the problem that Gravastars were invented to solve, disappears if the event horizon never forms. No horizon, no paradox, but that raises a new paradox. If Gravastars have internal structure, if they are more complex than black holes, why have we never detected that complexity? Why do all the compact objects we observe look like they obey the no-hair theorem? One answer is that we have not looked closely enough. The differences between a Gravastar and a black hole are subtle. The external gravitational field is identical. The lensing is identical. The orbits of nearby stars are identical. You have to look at the fine details, the ring-down signal after a merger, the spectrum of radiation emitted by the accretion disk, the response of the object to tidal forces from a companion. Those details are hard to measure. Current instruments are not sensitive enough. Future instruments might be. But until we have that data, Gravastars and black holes remain observationally indistinguishable. Another answer is that Gravastars are rare. Maybe most collapsing stars do form black holes. The conditions required for a vacuum phase transition are so specific, so finely tuned, that only a tiny fraction of collapses produce Gravastars. The rest produce black holes as expected. In that scenario, Gravastars exist, but they are uncommon. Needle-in-a-haystack objects. We would need to observe thousands of compact objects and analyze their properties carefully to find even one Gravastar. That is not impossible, just hard. And it requires a level of observational precision we do not yet have. A third answer, the one most physicists would probably lean toward, is that Gravastars do not exist. The hypothesis is mathematically interesting. It solves a problem that needs solving. but the physics required to make it work is too speculative, too far removed from anything we have observed. Exotic matter with negative pressure, vacuum phase transitions under extreme gravity, shell structures held together by surface tension at densities exceeding neutron stars. Every piece of the puzzle requires something we have never confirmed. Stack enough unconfirmed assumptions on top of each other, and eventually the structure collapses under its own weight. Not because any single assumption is obviously wrong, because the combined probability of all of them being right is vanishingly small. That is the skeptic's position, and it is a reasonable position. Extraordinary claims require extraordinary evidence. Gravastars are an extraordinary claim. The evidence so far is zero, yet the hypothesis persists. New papers appear every year. Some explore gravastars in modified gravity theories. F of R gravity, F of Q gravity. Brane-world scenarios where our universe is a four-dimensional surface embedded in a higher dimensional space. Each modification changes the Einstein equations slightly, and each change opens up new possibilities for Gravastar solutions. A paper published in 2024 described a nested Gravastar, a Gravastar inside another Gravastar. The authors called it a nestar. The outer shell contains an exotic core. The exotic core contains another shell. That shell contains another exotic core. Shell within shell within shell. The solution is mathematically valid. It satisfies the Einstein equations with the appropriate junction conditions. Whether it is physically real is another question. The nestar is an example of how flexible the mathematics can be. How many different configurations you can construct once you allow exotic matter and thin shells. The space of possible solutions is enormous, and most of that space has not been explored. The mathematical nightmares are not going away. Every time someone resolves one issue, another appears. Prove that Gravastars can be stable, and someone asks how they form. Model the formation process, and someone asks whether the phase transition is realistic. Justify the phase transition, and someone asks where the exotic matter comes from. Answer that, and someone asks why we have never detected it. The questions compound. The hypothesis survives because it has not been definitively ruled out. But surviving is not the same as thriving. Gravastars exist in a liminal space between possibility and reality. The mathematics says they could be real. The physics says maybe. The observations say nothing. And until one of those three pieces shifts, until we either detect a Gravastar, rule them out completely, or develop a theory of quantum gravity that tells us definitively whether vacuum phase transitions can happen during gravitational collapse, Gravastars will remain what they are now. A beautiful, frustrating, mathematically rigorous idea that may or may not describe anything in the actual universe. And that uncertainty, that refusal of the math to give a clean answer, is what keeps physicists coming back to the problem. Because if Gravastars are real, if they are out there hiding among the black holes we have catalogued, then we have been wrong about some of the most extreme objects in the universe for decades, and that possibility, however remote, is enough to keep the nightmare alive. We have been building a case for Gravastars as theoretical objects, mathematical curiosities that might exist if the right exotic physics turns out to be real. And now we arrive at the uncomfortable part. The part where you have to seriously consider the possibility that Gravastars are not just theoretical, that they are out there right now, that some of the objects astronomers have been confidently cataloguing as black holes for decades might not be black holes at all. that we have been staring directly at Gravastars, imaging them, measuring their masses, analyzing their gravitational waves, and calling them by the wrong name. Not because anyone made a mistake, because Gravastars and black holes look almost exactly the same from the outside. And almost exactly is close enough to fool every telescope, every detector, and every analysis technique we currently have. This is not paranoia. This is what the mathematics predicts. A gravastar with the same mass as a black hole produces the same gravitational field outside its surface. Identical, not approximately the same, not close enough that you need a really good detector to tell the difference. Exactly the same. General relativity is very clear on this point. The spacetime curvature outside a spherically symmetric mass distribution depends only on the total mass enclosed. It does not depend on what the mass is made of. It does not depend on whether there is a singularity at the center, or a shell of exotic matter, or a solid ball of neutrons. The exterior geometry is determined entirely by how much mass sits inside a given radius. A black hole with 10 solar masses and a gravastar with 10 solar masses, both spherically symmetric, both non-rotating, produce identical Schwarzschild spacetimes outside their surfaces. The gravitational pull is the same. The bending of light is the same. The orbits of nearby stars are the same. From any distance larger than the radius of the object itself, you cannot tell them apart by measuring gravity. That fact alone should make you nervous, because it means that every piece of evidence we have used to confirm the existence of black holes, stellar mass black holes, supermassive black holes, the whole catalogue, is also consistent with Gravastars. The Milky Way's central compact object, Sagittarius A star, weighs about 4 million solar masses. We know that because we have tracked stars orbiting it for decades. Some of those stars complete full orbits in less than 20 years, moving at several % of the speed of light. The orbits tell us the mass. 4 million suns compressed into a region smaller than Mercury's orbit. That is extreme, that is compact. And it is exactly what you would expect if the object were a supermassive black hole. But it is also exactly what you would expect if the object were a supermassive Gravastar. The orbits do not distinguish between the two. The gravitational field outside the object is the same either way. The Event Horizon Telescope imaged the black hole at the center of Messier 87 in 2019. 6.5 billion solar masses. The image shows a bright ring of light surrounding a dark center, the shadow. The dark region is about 2.5 times the size of the event horizon, created by light that either fell into the black hole or got trapped in unstable orbits just outside the horizon. The image confirmed decades of predictions. Black holes cast shadows. The geometry matches what general relativity says it should. That was a triumph, a beautiful, definitive confirmation that these objects exist and behave the way the theory predicts, except the image does not actually confirm that there is an event horizon. It confirms that there is a compact mass surrounded by a dark region where light does not escape easily. A Gravastar with the same mass would produce nearly the same shadow. The shell of a Gravastar sits just outside where the event horizon would be. Light passing close to the shell bends sharply, just like light near a black hole's horizon. Some of that light escapes, some of it does not. The resulting image, a bright ring around a dark center, looks almost identical. The differences, if they exist, are subtle. Small enough that with the resolution of the Event Horizon Telescope, you probably could not distinguish them. Some Gravastar models do predict differences in the shadow. If the shell emits light, if there is thermal radiation coming from the surface of the Gravastar, the dark center might be slightly brighter than a black hole's shadow. A black hole's shadow is perfectly dark because nothing comes out from behind the event horizon. A Gravastar's shell, being a physical surface at extremely high temperature, could glow, not brightly. The shell is under enormous tension and probably very cold compared to the gas in the accretion disk. But even faint emission from the shell could fill in the shadow slightly, making the dark center less dark. A paper published in 2021 analyzed this possibility and concluded that smooth Gravastars, models where the transition from the shell to the interior is gradual, struggle to match the observed shadow of Messier 87. The shadows those models produce are not dark enough. Too much light leaks out from the interior. But thin shell Gravastars, models where the transition is sharp and the shell is opaque, can match the observations. The shell blocks light from the interior. The shadow is dark. The image looks like a black hole. The distinction matters because it narrows the parameter space. Not all Gravastar models work, but some do, and those are the ones we need to worry about. Accretion disks are where things get interesting. A black hole surrounded by an accretion disk, a swirling disk of gas spiraling inward, produces characteristic radiation. The gas heats up as it falls, reaching millions of degrees in the inner regions. The hot gas emits X-rays. The spectrum of those X-rays, the distribution of energy across different wavelengths, depends on the temperature and density of the gas and on how close the gas can get to the central object before falling in. For a black hole, gas can spiral all the way down to the innermost stable circular orbit, the ISCO. Inside the ISCO, there are no stable orbits. Gas that crosses the ISCO falls straight into the event horizon in less than an orbital period. The location of the ISCO depends on the spin of the black hole. For a non-rotating black hole, the ISCO sits at 3 times the Schwarzschild radius. For a maximally rotating black hole, the ISCO can be much closer, down to about 1.5 times the radius in certain coordinate systems. The closer the ISCO, the hotter the gas, the higher the energy of the emitted X-rays. A Gravastar does not have an ISCO in the same sense because it does not have an event horizon. Gas falling toward a Gravastar hits the shell. What happens next depends on the properties of the shell. If the shell is perfectly reflective, if it bounces in falling matter back out, the accretion dynamics change completely. Gas would pile up near the shell, unable to fall through, and the radiation spectrum would look different. But if the shell absorbs in falling matter, if it accretes gas the way a neutron star accretes gas, the spectrum might look similar to a black hole spectrum. A study published in 2024 compared accretion disk spectra for black holes and Gravastars. The authors modeled how gas behaves near the shell, how it heats up, how it radiates. They found that Gravastars generally produce lower flux, lower peak temperatures, lower cutoff frequencies, and lower mass to radiation conversion efficiency compared to rotating black holes. The differences are measurable, in principle. The problem is that the differences are small, and they depend on parameters we do not know. The exact properties of the shell, the exact spin of the Gravastar, the exact accretion rate. Real astrophysical systems are messy. The gas is turbulent. Magnetic fields twist through the disk. The accretion rate varies over time. Trying to fit a theoretical model to real X-ray data and extract the subtle differences between a black hole and a Gravastar is extraordinarily difficult. It requires high-quality data, precise modeling, and a lot of luck. Jets complicate things further. Many accreting black holes produce jets, narrow beams of plasma shooting out from the poles at nearly the speed of light. The jets are powered by magnetic fields anchored in the accretion disk and twisted by the rotation of the system. The mechanism is called the Blandford-Znajek process for rotating black holes. Energy gets extracted from the spin of the black hole and channeled into the jets. The jets can extend for thousands of light years, carving cavities in the surrounding gas, lighting up radio galaxies and quasars. A Gravastar with an accretion disk would also have magnetic fields. The disk would rotate, the fields would twist, and in principle, the Gravastar could produce jets just like a black hole. The external dynamics, the behavior of the gas and the fields outside the object, are nearly identical. Whether the central object has an event horizon or a physical shell makes little difference to the jet formation mechanism. The jets do not care what is happening at the very center. They care about the magnetic fields threading through the disk. And those fields are the same whether the object is a black hole or a Gravastar. So jets, as spectacular as they are, do not help us distinguish between the two. Gravitational waves were supposed to be the smoking gun, the signal that would finally let us tell black holes and Gravastars apart. When two black holes merge, they emit gravitational waves as they spiral inward. The waves carry information about the masses and spins of the merging objects. After the merger, the resulting black hole rings down, settling into a stable state. The ring down emits gravitational waves at specific frequencies called quasi-normal modes. The frequencies depend only on the mass and spin of the final black hole, nothing else. Black holes have no hair. The ring down is a clean, predictable signal. Gravastars, if they exist, have internal structure. They have a shell. They have an exotic core. When two Gravastars merge, or when a Gravastar is perturbed by a passing gravitational wave or by accreting matter, the object rings at frequencies that depend on that internal structure. The quasi-normal modes of a Gravastar are different from the quasi-normal modes of a black hole, slightly different. The frequency shifts are small, but they are there, and in principle, if you could measure the ring-down signal with enough precision, you could detect those shifts and confirm that the object is a Gravastar. LIGO detected its first gravitational wave signal in September 2015. GW150914. Two black holes, 29 and 36 solar masses, merging into a single black hole of 62 solar masses. The signal was loud, clear, exactly what the models predicted for a black hole merger. The ring down was there. The quasi-normal modes matched the black hole prediction. A team led by Paolo Pani analyzed the ring down carefully in 2016, looking for deviations that would indicate something other than a black hole. They checked whether the signal could be consistent with a Gravastar merger. The conclusion was blunt. The notes measured with GW150914 simply do not match those that can be produced by Gravastars. The frequencies were wrong. The damping times were wrong. The signal was consistent with black holes, not Gravastars. That result was taken by many as a strong piece of evidence that black holes, not Gravastars, are what is actually merging out there, at least in this case. But that was one event, one merger. And the analysis assumed a specific model of how Gravastars ring. The quasi-normal modes depend on the properties of the shell and the core. Different Gravastar models predict different modes. If the shell is stiffer, the frequencies shift. If the core has a different equation of state, the damping changes. The parameter space is large. And while GW150914 ruled out some Gravastar models, it did not rule out all of them. Subsequent gravitational wave detections have painted a similar picture. Most events are consistent with black hole mergers. The ring-down signals match the black hole predictions, but the precision is not infinite. The detectors have noise. The signals are buried in that noise. Extracting the quasi-normal modes requires sophisticated data analysis and statistical techniques, and the uncertainties are still large enough that some Gravastar models remain viable. Not all, but some. The ones with parameters tuned just right to produce ring-down signals that are close enough to black holes that current detectors cannot distinguish them. GW190521 is worth mentioning because it has been flagged in the literature as a possible Gravastar candidate. The event, detected in May 2019, involved two objects with masses around 66 and 85 solar masses. The total mass was unusually high for a stellar mass merger, and some researchers proposed that the signal could be consistent with a Gravastar merger rather than a black hole merger. The idea is speculative, not accepted consensus. The mainstream interpretation is still that GW190521 was a black hole merger, possibly involving black holes formed from earlier mergers or from stars in environments with unusual metallicities. But the fact that Gravastar models can even be discussed as alternatives tells you something. The gravitational wave data, for all its precision, is not yet clean enough to rule Gravastars out completely. The door is still open, just barely, but open. Tidal disruption events are another potential discriminant. A tidal disruption event happens when a star wanders too close to a compact object and gets torn apart by tidal forces. The difference in gravitational pull between the near side of the star and the far side exceeds the star's own gravity. The star stretches, elongates, and eventually rips into a stream of gas. Half the gas falls toward the compact object, the other half gets flung outward. The infalling gas heats up and emits a bright flare of radiation, mostly in the ultraviolet and X-ray bands. Tidal disruption events are spectacular. They can outshine entire galaxies for weeks or months, and they are sensitive to the properties of the central object. How close the star can get before being disrupted depends on the object's radius. A black hole has an event horizon. A star that crosses the horizon disappears. You see the disruption happen outside the horizon. The gas brightens, and then some of it falls in and vanishes. A Gravastar has a physical surface. A star disrupted near a Gravastar would behave differently. The gas would hit the shell. Some of it might bounce back. Some of it might get absorbed. The radiation signature could differ. The problem is that tidal disruption events are rare. We have only observed a few dozen. And the physics of the disruption itself, the magnetohydrodynamics of the gas, the interaction with the accretion disk, is complicated enough that extracting subtle differences between a black hole and a Gravastar from real data is hard. Possible in principle, hard in practice. Photon spheres and light rings add another layer of subtlety. A photon sphere is a region around a compact object where light can orbit in circular paths. For a non-rotating black hole, the photon sphere sits at 1.5 times the Schwarzschild radius. Light traveling at exactly the right distance and angle can loop around the black hole indefinitely, neither falling in nor escaping. The photon sphere is unstable. A small perturbation and the light either spirals inward or escapes outward. But the sphere itself is a well-defined feature of the geometry. It is part of what creates the black hole's shadow. Light that passes just inside the photon sphere gets pulled into the event horizon. Light that passes just outside escapes but is lensed into a bright ring. A Gravastar also has a photon sphere because the exterior geometry is the same. Light can orbit just outside the shell. The shadow looks similar, but some Gravastar models predict an inner light ring, a second region deeper inside where light emitted from the shell or from the exotic core could loop around before escaping. If that inner light ring is bright enough, it would fill in the shadow slightly. The dark center would not be as dark. Thin shell Gravastars, where the shell is opaque and does not emit much light, do not have this problem. The shadow remains dark, but smooth Gravastars, where the transition from the exterior to the interior is gradual, could have a visible inner light ring. And that would be detectable, at least in principle, with high enough angular resolution. The Event Horizon Telescope achieved an angular resolution of about 20 microarcseconds for the Messier 87 image. That is extraordinarily sharp. Sharp enough to resolve features at the scale of the event horizon. But it is not sharp enough to detect every possible difference between a black hole and a Gravastar. Future observations, with more telescopes added to the array, with longer baselines, with observations at shorter wavelengths, could push the resolution even higher. The next generation Event Horizon Telescope, space-based interferometry. Those upgrades might be able to detect the subtle brightness differences in the shadow that would indicate an inner light ring. Might, not will. The differences are small. The signal-to-noise ratio is challenging, and you have to know what you are looking for. If you assume the object is a black hole and fit the data to a black hole model, you will get a black hole answer. If you test alternative models, Gravastars, boson stars, other exotic compact objects, you might find that some of them fit just as well. Or you might find that none of them fit. The only way to know is to do the analysis carefully, and that requires both the data and the theoretical framework to interpret it. The limitations of current detection techniques are real. Gravitational wave detectors like LIGO and Virgo are sensitive, but they have noise flaws. They can detect signals from merging compact objects out to distances of billions of light years. But the signal-to-noise ratio drops off with distance. Faint signals get buried in the noise. Extracting detailed information about the ring-down, the quasi-normal modes, requires a strong signal and sophisticated analysis. For most events, the uncertainties are large enough that you cannot definitively rule out alternatives to black holes. You can say the data is consistent with black holes, but consistent is not the same as proven. Electromagnetic observations, X-ray telescopes, radio telescopes, optical telescopes provide complementary data, but they face their own challenges. Accretion disks are turbulent, magnetic fields are tangled, the emission is time variable. Fitting a model to the data requires assumptions about the accretion physics, the magnetic field geometry, the spin of the central object. Change the assumptions and the best fit model changes. Gravastars and black holes can both fit the data if you tune the parameters correctly. That brings us to the uncomfortable question: should we be re-examining existing black hole candidates? Should we go back through the catalogue of stellar mass black holes, supermassive black holes, intermediate mass black holes, and ask whether any of them could be Gravastars? The answer is yes. Not because there is strong evidence that Gravastars exist, because the possibility has not been ruled out, and if Gravastars are real, if even a small fraction of the objects we call black holes are actually Gravastars, that changes everything. It changes our understanding of gravitational collapse. It changes the resolution of the information paradox. It changes what we think happens inside the most extreme objects in the universe, and it raises the possibility that we have been studying these objects for decades without realizing what they actually are. That possibility is worth checking. Some researchers have started doing exactly that, going back through gravitational wave data, reanalyzing X-ray spectra, testing whether Gravastar models can fit the observations as well as black hole models. The results so far are mixed. Some events are clearly more consistent with black holes. The ring-down modes match too well. The accretion disk spectra are too hot. The tidal forces are too strong. Other events sit in a gray area. The data is consistent with black holes, but not inconsistent with Gravastars. Those are the interesting ones. The cases where the distinction is not clean, where both interpretations remain viable, and there are more of those cases than you might expect. Not a majority, but enough to keep the question alive. Cygnus X1 is one of the most studied black hole candidates in the galaxy, a stellar mass compact object orbiting a blue supergiant star about 6,000 light-years from Earth. The compact object weighs about 21 solar masses. It accretes gas from the companion star, producing intense X-ray emission. Cygnus X1 has been observed for decades. Its mass, its X-ray spectrum, its variability all point to a black hole. The object is too heavy to be a neutron star. The emission is too energetic to come from anything less compact. But could it be a Gravastar? The external gravitational field would be the same. The accretion disk would look similar. The X-rays would be slightly different, maybe, depending on how the shell interacts with infalling gas, but the differences might be too small to detect with current instruments. Reanalyzing Cygnus X1 with Gravastar models is possible. Some teams have tried. The results are inconclusive. The black hole model fits well. The Gravastar model also fits, with the right parameters. You cannot definitively choose between them based on the data we have. That is frustrating, but it is honest. Sagittarius A star, the supermassive compact object at the center of the Milky Way, is another candidate worth re-examining. We have stellar orbits, we have radio images, we have X-ray flares from gas falling toward the object. Everything points to a supermassive black hole. But a supermassive Gravastar with the same mass would produce the same stellar orbits. It would produce a similar shadow, though the Event Horizon Telescope has not yet imaged Sagittarius A star with the same clarity as Messier 87. The flares could differ slightly if the shell emits or reflects radiation in ways that a black hole does not. But again, the differences are subtle. Testing whether Sagittarius A star could be a Gravastar requires data we do not yet have. Higher resolution imaging, better X-ray spectroscopy, possibly gravitational wave observations if the object undergoes a tidal disruption event, or if a smaller compact object falls into it. Those observations are coming. The next generation of instruments will provide the data. Whether that data will be enough to distinguish a black hole from a Gravastar is an open question. The difficulty of distinguishing them experimentally has been stated bluntly in the literature. A paper published in 2025 by Parucci and collaborators summarized the situation. It is very difficult to tell them apart experimentally. That is not a failure of the science. That is the reality of the situation. Gravastars are designed, by the very structure of the hypothesis, to mimic black holes as closely as possible. They have the same external gravitational field. They produce similar shadows. They emit similar radiation from accretion disks. The only differences are in the fine details, the ring-down modes, the inner light rings, the accretion efficiency, the tidal interactions. And those fine details are at the edge of what current instruments can measure. We are pushing the limits of observational astronomy and gravitational wave detection to try to see differences that might not even be there, or that might be so small that distinguishing them from noise requires data quality we will not achieve for years. That is where we are. Black holes and Gravastars look almost the same. Almost is not the same as identical. There are differences, theoretical differences, predicted differences, but whether those differences are large enough to detect and whether we have the tools to detect them is uncertain. The mathematics says Gravastars could be hiding among the black holes we have catalogued. The observations so far have not confirmed that, but they also have not ruled it out. We are standing in the middle of a zoo full of compact objects, some definitely black holes, some possibly Gravastars, and we do not have a reliable way to tell which is which. Not yet. The tools are improving. The detectors are getting more sensitive. The telescopes are achieving higher resolution. The data is accumulating. And eventually, probably within the next decade, we will have enough information to start narrowing the possibilities, to test whether the objects we see are consistent only with black holes, or whether some of them could be Gravastars, to check whether the universe has been hiding a completely different class of compact object right under our noses. And if the answer is yes, if even one of the objects we call a black hole turns out to be a Gravastar, then the questions start piling up. How many more are there? How common are they? Why did they form? What does that tell us about the physics of gravitational collapse? What does it tell us about exotic matter, vacuum condensates, and the limits of general relativity? Those questions are waiting. The answers, whatever they turn out to be, are sitting in the data, hidden in the gravitational wave signals, buried in the X-ray spectra, encoded in the shadows cast by light bending around objects so extreme that they warp spacetime into shapes we are only beginning to understand. And if Gravastars are real, if they exist, then the next question is unavoidable. What happens if we confirm it? What changes when we stop calling these objects black holes and start calling them something else? What does that mean for the universe we thought we understood? We have spent thousands of words building a case. The mathematics allows Gravastars. The physics, speculative as it is, does not forbid them. The observations, inconclusive as they are, have not ruled them out. And the uncomfortable reality is that some of the objects we have been confidently calling black holes for decades could be Gravastars wearing perfect masks. That possibility, however remote, sits at the edge of what we know and what we can test. And now we arrive at the question that matters. What if they are real? Not theoretically possible, not mathematically consistent, real. What if Gravastars exist out there in the universe right now, hiding among the black holes we have catalogued, and we confirm it? What happens then? What changes? And more importantly, what does their existence tell us about the universe we thought we understood? The paradigm shift would be immediate and profound. Black holes have been the cornerstone of extreme astrophysics for more than half a century. They are the objects that form when gravity wins completely. When a massive star exhausts its fuel and collapses, when nothing can stop the implosion, you get a black hole. Event horizon. Singularity. Information trapped forever behind a geometric barrier that nothing, not even light, can cross. That story is clean, it is definitive, and it is what every textbook teaches. Gravastars break that story. They say the collapse does not always go all the way. They say that at the last possible moment, when the core is about to cross the threshold into oblivion, something intervenes. Exotic matter floods the interior. A vacuum phase transition halts the implosion. The singularity never forms. The event horizon never appears. You end up with an object that looks like a black hole from the outside, but has a completely different internal structure. A shell of ultra-relativistic matter under enormous tension, wrapped around a core of exotic vacuum with negative pressure. No singularity, no information loss, no paradox, just a different kind of compact object that we have been confusing with black holes because they are almost indistinguishable. If Gravastars are confirmed, the first casualty is the singularity. Singularities have always been a problem. Not a small problem, a foundational problem. When the equations of general relativity predict infinite density and infinite curvature, that is not nature telling us something has truly become infinite. That is the equations telling us they have broken down. Infinities in physics are red flags. They signal that you have pushed a theory past its range of validity. Physicists have known this for decades. Roger Penrose and Stephen Hawking proved in the 1960s that singularities are generic features of gravitational collapse in classical general relativity. But the word classical is doing a lot of work. Classical general relativity does not include quantum mechanics. And at the scales where singularities form, quantum effects should matter. The singularity is a place where the theory stops working. It is not describing reality anymore. It is just telling you that you need a better theory. Gravastars provide an escape route. If the collapse stops before the singularity forms, if exotic matter or quantum effects or a vacuum phase transition stabilizes the core at a finite density, then the singularity never happens. You avoid the infinite curvature. You avoid the breakdown of the equations, and you end up with an object that general relativity can describe all the way through. No gaps, no places where the math gives up. The Gravastar is a solution that stays finite, that is elegant, almost too elegant, and it suggests something uncomfortable. It suggests that the singularities we have been worrying about, the ones sitting at the centers of black holes and at the beginning of the universe, might not be real. They might be artifacts of using classical general relativity in regimes where it does not apply. Remove the singularities and you remove some of the deepest mysteries in physics, but you also open new questions. If the collapse stops, what stops it? What is the exotic matter made of? Where does it come from? How common is the phase transition that creates it? Those questions do not have answers yet. But they are better questions than what happens at infinite density, which is not a question anyone can answer because infinite density is not a physical concept. The information paradox disappears if gravastars are real. The paradox, the one that has been tormenting physicists since Stephen Hawking discovered black hole evaporation in 1974, is this. Quantum mechanics says information cannot be destroyed. Black holes appear to destroy it. Everything that falls past the event horizon, all the details about the particles, the quantum states, the structure of the matter, vanishes from the perspective of the outside universe. When the black hole evaporates through Hawking radiation, the radiation is thermal, it carries no information. The information that went into the black hole is gone. That violates unitarity, the principle that quantum mechanics is built on. Break unitarity and the entire framework collapses. Physicists have spent decades trying to resolve this paradox. Proposals range from information encoding on the event horizon to holography to quantum entanglement between the interior and exterior. None of them are entirely satisfactory. All of them require either modifying quantum mechanics, modifying general relativity, or accepting that something deeply strange happens at the horizon. Gravastars sidestep the problem entirely. No event horizon, no paradox. Information that falls onto a gravastar does not vanish. It gets absorbed by the shell. The shell heats up. The energy spreads across the surface. The information is still there, encoded in the thermal state of the shell. Scrambled, yes, probably unreadable, but not destroyed. The gravastar preserves information because it does not have the structure, the event horizon, that causes the information to disappear. That is a clean resolution, almost suspiciously clean. It solves the paradox by denying that the thing causing the paradox ever forms. And it raises the question of whether the information paradox was ever a real problem or just a consequence of assuming that black holes, with their event horizons and singularities, are the only possible endpoint of gravitational collapse? If gravastars exist, the paradox might be telling us something simpler. Not that quantum mechanics or general relativity is wrong, that our assumptions about what forms during collapse are wrong. The search for proof is where things get practical. Confirming that gravastars exist requires finding an observational signature that distinguishes them from black holes. And that signature has to be something we can actually measure with instruments that exist or will exist in the near future. Gravitational waves are the most promising avenue. When two compact objects merge, they emit gravitational waves. The waves carry information about the masses, spins, and internal structure of the merging objects. After the merger, the resulting object rings down, emitting waves at specific frequencies. Black holes ring at quasi-normal frequencies that depend only on mass and spin. Gravastars, with their internal structure, should ring differently. The frequencies would shift, the damping times would change. If we could measure the ring-down with enough precision, we could detect those shifts. That would be the smoking gun, the signal that tells us the object is not a black hole. Current detectors are not quite there yet. LIGO, Virgo, and CAGRA can detect the ring-down, but the precision is limited. The uncertainties are large enough that small differences between black holes and gravastars get buried in the noise. But the next generation of detectors will be better. The Einstein telescope, a proposed European observatory with arms 10 kilometers long, buried underground to reduce seismic noise. Cosmic Explorer, a proposed upgrade to LIGO with arms 40 kilometers long. The Laser Interferometer Space Antenna, LISA, which will observe gravitational waves from space, free of ground vibrations and atmospheric interference. Those instruments will be significantly more sensitive than current detectors. They will be able to measure the ring-down with much higher precision. And if gravastars exist, if they are merging out there, those detectors should be able to see the differences. Should. Not will. The differences are subtle. The signal-to-noise ratio has to be high, and you need enough events to distinguish statistical fluctuations from real deviations. But the tools are coming. Within the next decade, maybe two, we will have the data. Electromagnetic observations provide another route. The Event Horizon Telescope imaged the shadow of the supermassive compact object at the center of Messier 87. The shadow is a dark region surrounded by a bright ring of light, created by the extreme bending of spacetime near the event horizon. A gravastar with the same mass would produce a similar shadow, but not identical. If the shell emits light, if there is thermal radiation coming from the surface, the shadow might be slightly less dark. If there is an inner light ring, a region where light emitted from the interior loops around before escaping, the center of the shadow could be brighter than a black hole's shadow. Those differences are small. They require very high angular resolution to detect. But the Event Horizon Telescope is being upgraded. More telescopes are being added to the array. Observations at shorter wavelengths are planned, and there is serious discussion of space-based interferometry, which could push the resolution even higher. Those upgrades might be able to detect the subtle brightness differences that would indicate a gravastar. Might. The uncertainties are real, but the possibility is there. Accretion disks are harder to use because the physics is messy. Gas falling toward a compact object heats up, becomes turbulent, generates magnetic fields, and emits radiation across a wide range of wavelengths. Modeling that process requires assumptions about the accretion rate, the magnetic field geometry, the spin of the object, and the properties of the gas. Change the assumptions and the predicted spectrum changes. Gravastars and black holes both produce hot accretion disks. The differences in the emitted radiation are subtle. Lower flux, lower peak temperatures, lower cutoff frequencies for gravastars compared to rapidly rotating black holes. But those differences are small enough that fitting a model to real data and extracting the distinction is difficult. Not impossible, just difficult. You need high-quality X-ray spectra, precise modeling, and a clear understanding of all the astrophysical processes involved. That is a tall order, but it is being worked on. Telescopes like NuSTAR and the X-ray Timing and Polarization Observatory, NICER, are collecting data. Future missions like Athena and Lynx will provide even better spectra. The data is accumulating, and eventually, with enough observations and sophisticated enough models, we might be able to distinguish gravastar accretion from black hole accretion. Eventually, a paper published in Physical Review D in June 2026 reported a gravastar formation model. The paper, authored by researchers working on quantum-improved spacetimes, described a scenario where quantum corrections to the Einstein equations prevent singularity formation during gravitational collapse. The corrections kick in when the curvature becomes very large, creating a repulsive pressure that halts the implosion. The core stabilizes in a gravastar configuration. A shell forms. The object settles into equilibrium. The paper was careful to note that the model is based on effective field theory, an approximation of quantum gravity that may or may not capture the full behavior of spacetime at extreme densities. But the result is significant because it shows that gravastar formation is not just a wild speculation. It is a consequence of taking quantum effects seriously in the context of gravitational collapse. If quantum gravity behaves even remotely like the model predicts, gravastars should form. The question shifts from whether they can exist to how often they form and whether we can detect them. The philosophical implications are where things get uncomfortable. A universe with gravastars is a universe where reality is more fragile than we thought. Black holes are stable. Once they form, they last effectively forever. They evaporate eventually, but the time scale is so long that it might as well be infinite for any practical purpose. A black hole with the mass of the Sun would take 10 to the 67 years to evaporate. That is a 1 followed by 67 zeros. A trillion years. The universe is only about 14 billion years old. Black holes formed in the early universe will still be there when the last stars burn out, when galaxies drift apart, when protons decay and the universe becomes a cold, empty void. Black holes are eternal. Gravastars are not. They are metastable, stable for now, stable as long as nothing disturbs them. But vulnerable. The shell is under enormous tension. The balance between the inward pull of gravity and the outward push of exotic matter is delicate. One good kick, a passing gravitational wave, a collision with another compact object, an accretion event that adds too much mass, and the balance breaks. The shell fails, the gravastar collapses. In less than a second, the entire structure implodes. You get a black hole, or possibly something worse. That possibility is unsettling. It means the universe could be filled with objects that look stable but are actually ticking time bombs. Objects held together by forces we do not fully understand, balanced on a knife edge, waiting for the right perturbation to push them over, and we would not know. From the outside, a gravastar looks like a black hole. It acts like a black hole. It gravitates like a black hole. You would have no warning that it is one bad day away from catastrophic collapse. That is the horror. Not the horror of inevitability, not the horror of something that is guaranteed to destroy you if you get too close. The horror of fragility. The horror of an object so massive, so powerful, so dense, that it warps spacetime into shapes that barely make sense, and yet it is held together by a shell a few hundred meters thick, under more tension than anything you can imagine. The wire is fraying, the shell is strained, and if it snaps, the energy release would be one of the most violent events in the universe, a burst of gravitational waves, a flash of radiation, and then silence, a new black hole where the Gravastar used to be, and you would never have seen it coming. Some Gravastar models evolve in even stranger directions. A paper published in 2011 studied the stability of Gravastars and found something unexpected. Under certain conditions, the Gravastar does not collapse into a black hole. It collapses into a naked singularity. A singularity without an event horizon. The paper called it the first time in the literature that a naked singularity emerges from a Gravastar model. Naked singularities are objects that most physicists believe cannot exist. Roger Penrose proposed the cosmic censorship hypothesis in 1969, which says that nature does not allow singularities to be visible. Every singularity is hidden behind an event horizon, clothed, not naked. But cosmic censorship is a conjecture, not a proven theorem, and the Gravastar model showed that under specific circumstances, the collapse can produce a singularity without a horizon. If that is real, if naked singularities can form, then the universe is even stranger than we thought. A naked singularity would be visible. You could see spacetime curvature becoming infinite at a point. You could watch the breakdown happen, and you could, in principle, send signals to and from the singularity. The causal structure would be bizarre. The implications for the rest of physics would be profound. And the fact that a Gravastar, an object designed to avoid singularities, can sometimes produce one anyway, tells you how delicate these structures are. They sit at the edge of stability, and the edge is not a safe place to be. Then there is the cosmological angle. A paper published in 2023 explored the connection between Gravastars and loop quantum cosmology. Loop quantum cosmology is a framework that applies ideas from loop quantum gravity to the early universe. One of its key predictions is that the Big Bang singularity, the point of infinite density and temperature where classical general relativity breaks down, is replaced by a big bounce. The universe does not start from a singularity. It contracts to a minimum size, bounces, and then expands. The bounce is driven by quantum effects that create a repulsive force at very high densities, the same kind of repulsive force that stabilizes a Gravastar. The paper argued that the mechanism preventing singularity formation in Gravastars is the same mechanism preventing singularity formation at the beginning of the universe. If Gravastars are real, it suggests that quantum effects can resolve singularities in multiple contexts, not just in collapsing stars. In cosmology too. That connection is beautiful. It hints at a deeper principle. A principle that says singularities, whether in black holes or at the Big Bang, are not real features of nature. They are artifacts of using classical general relativity in regimes where quantum effects matter. Resolve the singularities, and you get a universe that is finite and regular all the way through. No infinities, no breakdowns, just physics. But that principle comes with a cost. If singularities are not real, if quantum effects always step in to prevent them, then spacetime at very small scales or very high densities is not what general relativity says it is. It is something else. Something granular, something discrete, something with a minimum length scale where the smooth geometry of general relativity gives way to a quantum foam of fluctuating spacetime. We do not know what that something is. We do not have a complete theory of quantum gravity. Loop quantum gravity is a candidate, String theory is a candidate. Causal set theory is a candidate. None of them are confirmed. None of them make testable predictions we can check right now. But if Gravastars are real, if they form through a quantum mechanism that prevents singularities, then one of those theories, or something like them, has to be correct. The existence of Gravastars would be indirect evidence for quantum gravity, not proof, but a strong hint. A sign that the universe is telling us something about how space-time works at scales we cannot yet probe directly. The existential questions pile up. If Gravastars exist, what does that say about the nature of space-time? General relativity treats space-time as a smooth, continuous geometry. You can zoom in as far as you want, and the geometry stays smooth. But quantum mechanics suggests otherwise. At the Planck scale, about 10 to the minus 35 meters, space-time should become grainy, fluctuating, uncertain. The smooth fabric tears apart into discrete chunks, a quantum foam. Gravastars, if they are real, are probing that regime. The shell sits at densities where quantum effects should dominate. The exotic matter in the core is behaving in ways that classical physics does not predict. The object as a whole is a laboratory for physics we cannot recreate on Earth. And if the object is stable, if it can sit there for millions or billions of years without collapsing, then space-time at those densities is not as fragile as the classical equations suggest. It can hold together. It can resist the crushing force of gravity. It can avoid the singularity. That tells us something. It tells us that space-time, at its most extreme limits, has mechanisms we have not accounted for. Mechanisms that push back, that stabilize, that prevent the worst outcomes, and that raises the question of how many other places in the universe those mechanisms are operating. How many other contexts where we think singularities form, black holes, the Big Bang, the interiors of neutron stars, might actually be situations where quantum effects prevent the singularity and produce something else instead. The ultimate horror is not the Gravastar itself. The horror is what the Gravastar represents, a universe where the things we thought were solid, stable, eternal, are actually fragile. A universe where the most extreme objects, the ones we have been studying for decades, might not be what we think they are. A universe where reality itself, at its most fundamental level, is held together by forces and fields we have never confirmed exist. Exotic matter, negative pressure, vacuum condensates, phase transitions in empty space. Those are not things we have seen. Those are things the equations allow. And if Gravastars are real, it means the universe is using those exotic ingredients. It means nature has access to a toolkit we have barely begun to explore. And it means that everywhere we see a compact object, everywhere we see a black hole candidate, we should be asking whether that object is really a black hole or something stranger. Something that wears a black hole's face but hides a different interior. Something fragile masquerading as eternal. And here is the part that should keep you awake at night. If Gravastars are common, if a significant fraction of the compact objects we have catalogued are Gravastars rather than black holes, then the universe is filled with metastable structures sitting at the edge of collapse, millions of them, billions of them. Each one a shell under tension, wrapped around a core of exotic matter, balanced so delicately that a single gravitational wave could set off a cascade. The shell fails, the Gravastar collapses, the collapse releases energy. That energy propagates outward as gravitational waves. Those waves hit neighboring Gravastars. They oscillate. Some of them stabilize, some of them fail. A chain reaction, not immediate, not fast, but spreading through clusters of compact objects over millions of years, one collapse triggering the next. A cascade of failures rippling through the dark corners of the galaxy. We would not see it happening. We would only see the aftermath, a sudden increase in gravitational wave detections, a burst of high-energy radiation from the centers of galaxies, and then, slowly, a shift in the population of compact objects. Fewer Gravastars, more black holes. The metastable structures converting, one by one, into the stable objects that can last forever. That scenario is speculative, wildly speculative, but it is not ruled out by the physics. If Gravastars exist, and if they are as fragile as some models suggest, then a cascade is possible. Not likely, but possible. And the fact that it is even a possibility, the fact that the universe could contain structures so precariously balanced that disturbing one could eventually disturb them all, is unsettling. It suggests a cosmos that is less stable than we assume. A cosmos where the ground beneath our feet, or rather the space-time fabric everything rests on, is not as solid as it looks. Where the darkest, densest objects, the ones that should be the most permanent, are actually the most vulnerable. And where the simple act of observing them, of sending probes or gravitational waves or radiation toward them, could be enough to tip the balance. That is the cosmic horror. Not monsters from outside, monsters built into the structure of reality itself, held together by tension and exotic matter, waiting. The confirmation, if it comes, will not arrive as a single dramatic discovery. It will be a slow accumulation of evidence, a gravitational wave event with a ring-down signal that does not quite match the black hole template. An X-ray spectrum that fits better with a Gravastar model than a black hole model. A shadow image with subtle brightness features that hint at an inner structure. Each piece of evidence on its own will be ambiguous, uncertain, consistent with Gravastars, but not conclusive. But put enough pieces together and the picture will shift. The community will start to take the possibility seriously. Papers will be written reanalyzing old data. New observations will be designed to test specific predictions, and eventually, probably years or decades from now, the consensus will change. Some of the objects we call black holes will be reclassified. Not all of them, probably not even most of them, but some. And that will be enough to change the conversation, to force a re-evaluation of what happens during gravitational collapse, to open the door to exotic matter and quantum gravity effects and vacuum phase transitions as real, observable phenomena. Not speculative ideas, real physics. The paradigm shift will ripple outward. Textbooks will be rewritten. Courses on general relativity and black hole physics will add chapters on Gravastars. Researchers will shift their focus. New questions will replace old ones. Not what happens when you fall into a black hole. What happens when you hit the shell of a Gravastar? Not how do black holes evaporate? How do Gravastars store and release information? Not do singularities exist? How does space-time avoid them? The shift will take time. Paradigms do not change overnight, but they do change. And if Gravastars are real, the change is coming. And when it does, when the first Gravastar is confirmed, when the first object is definitively identified as something other than a black hole, we will look back at decades of observations and realize we were staring at the answer the whole time. The signals were there, the clues were there. We just did not know what we were looking at. We saw black holes because that is what we expected to see. We fit the data to black hole models because those were the models we had, and we missed the possibility that some of the objects hidden among the hundreds of black hole candidates were something stranger, something held together by forces we are only beginning to understand, something that challenges the idea that gravitational collapse always ends the same way, something that says the universe is more complicated, more fragile, and more terrifying than the clean story we have been telling ourselves for half a century. That is the Unveiling, not a monster from outside, a monster we built into our theories and then overlooked because it wore the right mask. And now, finally, we are starting to pull the mask off, slowly, carefully, one observation at a time. And whatever we find underneath, black hole or Gravastar or something else entirely, will tell us what the universe is really made of at its most extreme edges. And the truth, whatever it is waiting in the dark. So here is where we are. Somewhere in the universe, right now, there is a compact object, a dark thing, a gravitational monster sitting at the center of a galaxy, or orbiting a companion star, or drifting alone through the void. From a distance, it looks like a black hole. It gravitates like a black hole. It lenses light the same way, casts the same shadow, pulls stars into the same tight orbits. Every measurement we can make from out here says black hole. And maybe it is. Maybe the singularity is real, the event horizon is there, and everything we think we know is correct. Or maybe the object is something else. A shell of matter under tension beyond comprehension, wrapped around a core of exotic vacuum, pushing outward with the force of dark energy. A Gravastar. An object balanced so precisely between collapse and explosion that even the word stable feels generous. And we would not know the difference, not with the tools we have today, not without getting closer, not without measuring the fine details of how it rings when disturbed, or how it interacts with infalling gas, or whether the shadow it casts is perfectly dark, or faintly, almost imperceptibly, less empty than it should be. That uncertainty is not a failure, it is the frontier. The edge where observation meets theory, and neither one has the final word yet. Black holes were theoretical for decades before we confirmed them. Gravitational waves were theoretical for a century. The idea that reality could be stranger than we currently believe is not new. It is how physics works. You build a model, you test it, and sometimes the universe hands you data that does not quite fit. A signal that is almost right, but not exactly. A shadow that is almost dark, but not perfectly. And you have to decide whether to adjust the model or discard it. Whether the thing you are looking at is what you think it is, or something wearing its face. Gravastars are that question made physical. They are the possibility that the most extreme objects in the universe, the ones we thought we understood, are not what we think. That the collapse does not always go all the way. That singularities, the places where our equations break and reality becomes infinite, are not real. That spacetime, at its limits, has mechanisms we have not accounted for, mechanisms that push back, that stabilize, that prevent the worst outcome and leave something finite behind. Something strange, something fragile. Something held together by forces we have never confirmed exist, but that the mathematics allows and the observations have not ruled out.